¿Aló? ¿Aló?
Micrófono. Sí, sí. Okay. Good morning. Welcome everybody to the second day of this conference. And our first speaker this morning will be Nicolas Andruskiewicz, and he will talk about Noetherian enveloping algebra, simple gradually algebra.
Thank you, Glass, and good morning, everybody. First of all, I would like to thank Claudia and Alessandro for the kind invitation. I was told that I should not congratulate Claudia, so sorry, Claudia, I congratulate you. So first of all, I would like to explain why I am interested in this problem. Let me fix an algebraically closed field of characteristic 0. It is well known that there are some classes of groups that can be described in terms of Hopf algebras. For instance, an affine algebraic group is the spectrum of a finitely generated commutative Hopf algebra. And actually, there is a category of, there is an anti-equivalence of categories between the category of finitely generated commutative Hopf algebras and the category of affine algebraic groups. This appears in a paper by Cartier in '62. Also, it can be shown that the compact group is the spectrum of a commutative unital C-star Hopf algebra. Now, Drinfeld, in his seminal paper in '86, says that the category of quantum groups should be understood as the opposite to the category of Hopf algebras without commutativity with bijective antipode. For instance, the category of finite quantum groups is the opposite to the category of finite dimensional Hopf algebras, and therefore it is equivalent because this category is, via going to the dual, is equivalent to its opposite. So the question I was thinking for many years is what is the right definition of algebraic quantum group, which is, for me, it's not yet clear what should be the right definition. But there are some conditions one has to take into account. One of them is to be affine, which is a jargon word for finitely generated as an algebra. Noetherian, which is the ascending chain condition on left ideals or on right ideals, because if you are looking at Hopf algebras with bijective antipode, it will be left Noetherian if and only if it will be right Noetherian. And there is the notion of algebras with finite Gelfand-Kirchhoff dimension, which means that given an associative algebra, one defines by this strange rule the Gelfand-Kirchhoff dimension of A as the supremum over all finite dimensional vector space of this formula. And well, because of an important paper by Marc Rousseau in the 90s, I was thinking that maybe finite Gelfand-Kirchhoff dimension is the right notion of a affine algebraic group. But let me show you why these three conditions interact in the classical examples. So if you have a commutative Hopf algebra, then A is Noetherian if and only if it is affine. One implication is the Hilbert-basis Sachs, probably is the beginning of the story of Noetherian algebras. And the other implication is a theorem by Molnar. And in any case, these two conditions are imply, these two equivalent conditions imply that the Gelfand-Kirchhoff dimension of the algebra is A, and actually this is the dimension of the spectrum of A also, the algebraic group which is behind. And if the Gelfand-Kirchhoff dimension is finite, this does not imply that A is affine. For instance, you can take the group algebra of the group of roots of unity. Since this is a filtered union of finite dimensional Hopf algebras, the Gelfand-Kirchhoff dimension will be 0, but it is not affine. So let me go to co-commutative Hopf algebras. Since we are assuming characteristic 0 and algebraically closed, there is a well-known theorem that the structure of these co-commutative Hopf algebras reduces to the structure of Lie algebras and groups acting on them, namely that any co-commutative Hopf algebra is of the form the enveloping algebra of a Lie algebra, semi-direct product, a group algebra. So what happens with these conditions in the separate cases of group algebras and enveloping algebras? Suppose that G is a finite degenerated group, so that the group algebra will be affine. Then there is a very famous theorem by Gromov saying that the Gelfand-Kirchhoff dimension is finite if and only if G is nilpotent by finite. Actually, Gromov proved one of the implications. The other was known before by work of Milnor and Wolf. And what does it mean, nilpotent by finite? It means that there is a nilpotent normal subgroup of finite index. And on the other hand, being nilpotent by finite implies that it is polycyclic by finite. Polycyclic by finite means that it is solvable and every subgroup is finitely degenerated. And this is strict, so not every polycyclic by finite is nilpotent by finite. And why I mention polycyclic by finite? Because if the group is polycyclic by finite, then the group algebra will be Noetherian, and the converse is in principle open. However, if the group G is linear, meaning that it can be embedded in a GLN for some n, then it is known that the converse holds. This is a theorem by Tits. So somehow when I arrived to this point, I started to doubt whether one should leave out polycyclic by finite groups from the consideration by imposing the notion of finite Gelfand-Kirchhoff dimension as the alternative to an algebraic group, as the definition of algebraic quantum group. So let me go now to the problem of the talk. If G is Lie algebra, then the Gelfand-Kirchhoff dimension of U of G is easy to see that this will be finite if and only if the dimension of the Lie algebra is finite. And of course, this implies that the enveloping algebra is Noetherian. However, and the Gelfand-Kirchhoff dimension will be the dimension of G. However, the converse problem, whether U of G Noetherian implies the dimension of G is finite, is an open problem. It was stated the first time by Amajo and Stewart, and then it was asked by many specialists like Ken Brown here, Dixmier, Latishev, and apparently other people also asked this question. I don't know. So to finish this part of motivation, I would like to mention a question by Ken Brown. If you have a Hopf algebra which is affine, finitely degenerated, and has finite Gelfand-Kirchhoff dimension, does it follow that H is Noetherian? I believe that the answer is yes, but I do not see how to prove it without some classification results or some knowing more from the structure. But maybe this is, I do not know enough to say this. Now, the second part of the talk is about graded Lie algebras of finite growth. I focus on this because for infinite dimensional Lie algebras, there is no structure known, which is natural. So where one can start to work with the structure to prove anything. So what is a graded Lie algebra? Is a Lie algebra with a graded decomposition such that the bracket of Ln with Lm is contained in Ln plus m. And I will assume it's not absolutely necessary, it can be reduced to this case. So I will assume the dimension of the homogeneous components are all finite. Now I have a function, this gives a function which sends to n the dimension of the homogeneous component Ln, and one says that L has finite growth if this function n to the dimension of Ln is bounded by a polynomial. And the following result was conjectured by Victor Katz and was proved by Olivier Mathieu in a series of very nice papers already many years ago. He proved the following: if you have a graded Lie algebra of finite growth and it is simple in the sense that it has no graded ideal, then the Lie algebra has to be isomorphic to one of the following: or a finite dimensional simple Lie algebra, or a loop algebra, which means something like G, where G is finite dimensional simple, extended to the ring of Laurent polynomials, or some variation of this that I do not want to explain in this moment. Then it could be also a Cartan Lie algebra, or it could be the centerless Virasoro Lie algebra. So what is a Cartan Lie algebra? The Cartan Lie algebras are the main example is the algebra called Wn, which is nothing but the algebra of derivation of the polynomial ring in n variables, and some Lie subalgebras of Wn that have to do with taking some concat forms or some specific geometric information. The centerless Virasoro Lie algebra is the algebra of derivations of the ring of Laurent polynomials in one variable. It comes with the grading, and the W1, which corresponds to the subalgebra, which is spanned by the homogeneous components of degree bigger or equal to -1. For notational convenience, I said W plus, the direct sum of Wn for n bigger or equal than 1. So these are essentially the important examples. Now, what about Noetherian enveloping algebras? Suppose that L is a Lie algebra. If L is abelian infinite dimensional, then the associated then it is U of L will be the polynomial algebra in infinitely many variables, and then it will not be Noetherian. And if L contains a free, or if it is a free Lie algebra in at least two generators, it could not be Noetherian also. Therefore, this bounds a lot the possibility of having Noetherian enveloping algebras. On the other hand, if U of L is Noetherian, then L satisfies the ascending chain conditions on Lie subalgebras. It is finally represented. The dimension of the homology groups are all finite. If you have a subalgebra of L or a quotient of L, then this subalgebra or quotient will be also Noetherian. And if L is a Lie subalgebra which has finite codimension inside the Lie algebra L prime, then L prime will also be Noetherian. a breakthrough paper came more or less 12 years ago, was published in 2013, but appeared 1 year before by Susan Sierra and Chelsea Walton. They proved the universal enveloping algebra of the bit algebra W1 is not Noetherian. In fact, as I said, if a Lie algebra is big, meaning it contains a big abelian subalgebra or a free Lie algebra in more than one generator, then it will be Noetherian. So one has to focus probably on small examples, and this is the smallest simple example in the setting of finite growth. So this is a very important theorem. I mean, it goes to the point. And as a corollary, they showed by inspection that every infinite dimensional simple graded Lie algebra of finite growth, and by the theorem of Mathieu in the list before, then U of L is not Noetherian. And Busaglo extended this to Krichever-Novikov Lie algebras, which is the algebra of derivation on the functions of an algebraic curve. So what is our main result? Suppose that L is a simple z to the n graded Lie algebra without assuming anything on the growth, then UL, the enveloping algebra of L, is not Noetherian. I would like to share with you the scheme of the proof, which is based mainly on ideas of the paper by Mathieu from '92. So let me start by a Z-graded Lie algebra. Take inside L0, so L0 is a finite dimensional Lie algebra that acts on each of the homogeneous components, and therefore one can take a Cartan subalgebra as in the book of Bourbaki. Given a linear form alpha on H and n in zeta, we set L alpha n as the generalized eigenspace of alpha inside Ln. And for notational convenience, this alpha n is denoted alpha tilde. So it's it's just a notation. Then the set of roots is, as usual, the alpha tilde such that L alpha tilde is not zero. Zero is a root for us. And the root lattice is the subgroup inside H dual times zeta generated by the roots. And the rank of the Lie algebra is the rank of this root lattice. With this notation, one goes through several classes. The first class is called the class V, following the notation of the paper by Mathieu. It says that if the rank of L is 1, and if delta lies inside some Z alpha tilde, where alpha tilde is alpha n, but alpha is 0, then a lemma from the paper by Mathieu says that L is not finitely generated. And I already observed that if U of L is Noetherian, then it should be finitely generated, so U of L is not Noetherian. The class S comes from, where S comes from string, is the class where the rank is 1, but is not in the previous class. In this case, there is a theorem which is essentially contained in Mathieu, but we had to reprove it again, saying that if you have a simple Z-graded Lie algebra of class S, and L is finitely generated, then either L is isomorphic to SL2, W1, or W, or L contains a non-abelian free Lie algebra. Since using the theorem by Sierra and Walton, we can conclude that if you have a simple Z-graded Lie algebra of class S, then U of L Noetherian implies that L is SL2. The third step is when the rank of L is bigger or equal than 2. In this case, we prove that if it is simple Z-graded algebra of rank bigger or equal than 2, if U of L is Noetherian, then L is finite dimensional. Then we proved another lemma saying that if a simple Z-graded Lie algebra is not simple as a Lie algebra, then it contains an infinite dimensional abelian subalgebra, and then U of L is not Noetherian. The final step of the proof is about we fix a vector M1, Mn, such that L, so here I am going to the Z to the n graded setting, such that Lm is different from 0, and one of the entries is not 0, say M1. Then change the gradient of L as follows. Keep L as the Lie algebra, but take the L prime M as the direct sum of all homogeneous components of degree M, M2, Mn, where M2, Mn are arbitrary. We can assume by another lemma, which I not explain it here, that the homogeneous components of L prime are finite dimensional. Then the previous lemma finished the proof. Okay, so once we proved this, what remains to be done? The first observation is the following. One could naively think that you have, if you know the theorem for simple ones, then you take an arbitrary graded Lie algebra, simple or not, and you take a quotient, and you say, okay, the quotient will be simple, then it could not be Noetherian. However, the quotient could be finite dimensional. So what remains to be done in the graded setting is to prove the theorem for Lie algebras such that every maximal graded ideal has finite codimension. And we believe that this can be done, but haven't achieved yet. On the other hand, passing from the non-graded case to the graded case seems very difficult, and this is already the problem when you cannot go from the symmetric algebra to enveloping algebra, so it is kind of very difficult. And I would like to finish mentioning a question. I asked this, I was in China and worked with Mathieu there with him in the Institute of Selmanov, and I asked Selmanov about this question, and he told me, the following is not known. Does there exist an infinite dimensional Lie algebra such that any two linearly independent elements is generated? And if such a Lie algebra exists, it will be very difficult to prove that it is Noetherian or not Noetherian, I believe. Thank you very much.
It's a remark rather than a question about the part of Nicholas's early remarks on conjecture, open questions. On the group algebra situation, the question of whether the theory in group algebra the group has to be polycyclic by finite. There has been some recent progress on this, which maybe not everybody knows about. Some group theorists let me think of their names, Bartholdi, Keelak, Kropholler, maybe one other. They showed that if the group algebra is Noetherian, the group has to be amenable, which is a very big improvement on what we knew before. Amenable is a condition on groups which was defined by von Neumann and is very important currently. And maybe actually connection with Zelmanov's question there. I mean, these are kind of like his Lie algebras there. Conjectured Lie algebras are Lie algebra versions of Tarski monsters, which are well-known horrible groups which do exist, but they're not amenable. So although they have the maximum condition, they're ruled out. So there are situations in the group theory which are better than the Lie algebra situation.
Okay, any other question, remarks? If not, let's thank the speaker again. Okay, next speaker will be Marcelo Aguiar, and he will talk about Ekman-Hilton argument and Monoidal categories.
Thank you, class. Thank you, Claudia and Alessandro, for this nice invitation. It's a very enjoyable conference in a beautiful place, so I'm very happy to be here. So I am Marcelo, and Javier Coppola is at the University of Uruguay. This is joint work with him that I'll be presenting. So the talk is about the Ekman-Hilton argument and variants and versions of that aimed at a particular application that I'll discuss in a minute. But I decided to start by recalling the classical Ekman-Hilton argument. It's something really simple and basic, and I guess we've all seen at some point, but this is one formulation. It's a purely algebraic statement. We have a set with two operations denoted by two symbols like plus and times. And these are the only axioms that we require. So each of the operations has a unit element. And then the two operations are related by means of this axiom that is not the usual axiom for a ring. It is not distributivity. It is something else. It is this. It can be read as follows. This is simply stating that each operation is a morphism with respect to the other operation when you regard the Cartesian product. So if the underlying set is X, and you view each operation as a map from X times X to X, and you view the Cartesian product as you endow the Cartesian product with the coordinate-wise operation, then this is simply expressing that each one is a morphism with respect to the other. Okay, if you have these things, then there's a bunch of striking consequences that take place. The units must agree, the operations must agree, and either operation then is commutative. In fact, it also follows that they are associative. So all of these consequences follow from these axioms. This is called an argument because it was implicit or included in the proof by Ekman and Hilton of the commutativity of the higher homotopy groups. That's the classical origin of this. But it is an algebraic statement, and that's what it is. Okay? So that's the Ekman-Hilton argument. And it's something that can be used across mathematics for proving the commutativity of many products that arise. So that's what I want to turn to. I present this as the goal or maybe the motivation for the talk. It won't be the focus because if I'm lucky and I have time, I'll get to it towards the end, but I want to get it done now. So this is a familiar fact for people who work with Hochschild cohomology. people who work with bialgebras or Hopf algebras, if you have a bialgebra and you view the ground field or the ground commutative ring as a bimodule over H, trivially, by means of the co-unit of the bialgebra, well, you have a bimodule over an algebra, so you can then consider the Hochschild cohomology of the algebra H with coefficients in K. And it's a fact, well, this is a ring, always for any algebra and any, well, for any algebra with this type of coefficients, then this is a ring. It carries a product called the cup product. It's basically defined by concatenation of cochains, so I'm assuming some basic familiarity with Hochschild cohomology. And in this situation, when you're looking at a bialgebra, and Hochschild cohomology of a bialgebra, the cup product is commutative in the graded sense. We would like to explain this fact from the perspective of the Ekman-Hilton argument. Now, not every commutativity that arises in mathematics should be explained by the Ekman-Hilton argument, but there is a reason in this situation to expect something like this to be possible. It is the following, that we're dealing with a bialgebra here. That plays a role in this wouldn't be true if I were looking at Hochschild homology of an algebra, say an augmented algebra, so that I can view K as a bimodule over H. It wouldn't be true, but it is true for bialgebras. So the coproduct is playing a role. And one way in which one can then expect Ekman-Hilton to come in is as follows. The cup product has nothing to do with the coproduct. The cup product is defined by concatenating cochains. So cochains are maps from H dot tensor n times with itself to K, that would be an n cochain. And this is the direct sum of all the cochain spaces. But the commultiplication of H allows us to endow each cochain space with a convolution product. So in that manner, one has a second operation on this space besides the cup product. And then one could imagine that that's the reason why the cup product ends up being commutative as an instance of Ekman-Hilton. However, that doesn't quite work. It doesn't work for one reason or another, depending on how you formulate things. But what happens really is that if you really force, see what I mentioned about convolution is really defined internally within each space of cochains. One can then cook up a product on the whole direct sum of the cochain spaces, but if one does that, then the axioms that we needed for Ekman-Hilton don't hold. So there are obstacles there. However, there is something that can be done, and that's what I would like to discuss. In fact, what we're going to do is we're going to generalize this fact. We're going to formulate a version of this that holds more generally, not just for Hochschild cohomology of bialgebras, but something that requires us to be working in the setting of duoidal categories. And at the same time, we're going to extend this fact, which is about Hochschild cohomology, to the level of Hochschild cochains. So, in fact, even to the cosimplicial level. So I'll explain a little bit of that later if that doesn't make sense now. But really, the main focus of the talk will be on the basics of duoidal categories, which could be more useful if you haven't encountered them before, okay? Maybe you can keep in mind that I have an application in mind, but we can just go over these basic definitions and examples, and perhaps that's something worthy of taking home from the talk. So what is a duoidal category, or a duoidal structure on a category? It's just a twofold version of a monoidal category. We all know what monoidal categories are, and these duoidal categories are also familiar and simple to define. So you have two monoidal structures on the category, so two tensor products with the axioms for a monoidal category. In particular, each one has a unit object. And then the two monoidal structures should be linked by means of a natural transformation of this sort called the interchange law. So this is a part of the structure. You have to be given this family of maps. And you see that what happens is that there is an interchange of the middle factors. This is called the interchange law, or the middle interchange law. And there are also morphisms involving the unit objects that are part of the structure. So the unit objects J and K for the two monoidal operations. So there are various axioms. This is an evolved version of a definition given by Valtiano and Fyodorovich. They didn't have the complete definition. The complete definition was given by Richard Gardner, and in my work with Shamil Mahajan, independently, more or less at the same time. Baltiano and Fyodorovich had something like this, but they didn't deal correctly with the unit object. They assumed that the two operations had the same unit and that all these maps were identities implicitly. And that's not a very good thing to do because most examples do not satisfy those assumptions that they were requiring. So their theory was a bit of missing of examples. But we do have a complete definition that is more flexible. Two double categories. Right, so interchange laws resemble something that appears when one is dealing with a double category. There is a relation, and that's a good question, I can say a word. What is that one has in a double category? So a double category has cells which are squares, right? And they can be composed both horizontally and vertically. And then there is the interchange law, which is an equality, actually, between two ways of composing four squares, right? When you have a big square divided into four smaller squares, you can compose first horizontally and then vertically, or the other way around, and those two should be equal. But here, you see, we have a morphism, and this morphism is not even required to be invertible. So the way you can think of this is, just as a monoidal category is the one-object version of a bicategory, this wants to be the one-object version of a double category. But for that to be true, you need to be speaking of double categories in a weak sense, not in the usual sense, which is strong, in which one has an equality. And the definition of double categories in the weak case has not been worked out fully. In fact, there is very recent work by some people on that, on what the weak version of double categories should be. So, yeah, so that's... All right, so, again, this is the interchange law, just a picture depicting the interchange law, not very important. I want to emphasize this point. Nothing is required to be invertible here. The interchange law or the other unit maps need not be invertible. And if you have a duoidal category, the order in which you give the operations matters, because in interchange law you see maps one way and not the other. So if you switch the two operations, the order of the two operations, you no longer have a duoidal category, because you won't have an interchange law mapping the other way around, not necessarily. And I didn't spell out the axioms, but they can be packed into these two assertions. Each operation should be monoidal with respect to the second operation should be monoidal with respect to the first, and the first operation should be comonoidal with respect to the second. So what is monoidal and comonoidal? When you view the operation as a functor, it should be a monoidal functor, also called lax monoidal functor. And this one should be a colax monoidal functor, also called comonoidal. So for those of you familiar with monoidal categories, that has a meaning. So briefly, there are some commutative diagrams that must hold for us to have a duoidal category. Okay, a bunch of examples. So there are many examples, so I just chose 2 or 3 here. So the category of graded modules graded by a monoid M. So you fix an ordinary monoid, a set with an operation that is associative and unital, and then you look at sequences of modules over our ground ring indexed by elements of the monoid. On that category of sequences of graded modules, there are 2 natural operations. So you can form a convolution type of operation like this, right, in which you have 2 sequences x and y, you have to define a third sequence, so you have to define each component of the sequence, and you use this convolution formula, akin to the Cauchy product of sequences, so we refer to this as the Cauchy product of graded modules. And then, of course, for forming the convolution, you are using the fact that our indexing set N is a monoid. Now, if you ignore the fact that you have a monoid, you can always do this. You can just multiply the sequences term-wise. So this would be analogous to the Hadamard product of sequences, right? If this is analogous to the Cauchy product of sequences. And these 2 operations interact nicely. They do turn this category into a duoidal category, meaning there is a natural interchange law that one can define. So if you compute both sides, the domain and the codomain of the interchange law, in this example, you find that one naturally sits inside the other. Just by switching the 2 middle factors, you get an inclusion of one into the other. Not an isomorphism, but an injection. So there is a natural interchange law. This is what the unit objects are, and you see that they're different. This is an example of a duoidal category. Another interesting example is this one. Some people here, or maybe online, but there are people online that are very familiar with this, and here too. But this is one interesting example. You fix a commutative algebra, and then you look at bimodules over that commutative algebra, which, given that R is commutative, can be identified with R tensor R modules. And then you define these two operations. You have two of these, x and y, and you see you can tensor over R tensor R, because both of them are modules over R tensor R, because they are bimodules over R. And then you can turn this again into an object of the same kind, because R tensor R, after all, is a commutative ring, so this will also be a module over R tensor R, this whole thing. But you can also tensor them using the right module structure of x and the left module structure of y, and use the fact that you have the remaining left module structure of x and the remaining right module structure of y to turn this again into an R bimodule. So you have these two different operations. Each one has a different, a unit object, and they're different. And there is again a natural interchange law. There is again a canonical map that one can define from the two sides, the domain and the codomain of the interchange law. This is a duoidal category. Here's another family of examples. If you start from a braided monoidal category, some braiding beta, then you can do the following. You can duplicate the monoidal operation. So you define the two new monoidal structures to be the same as the given one, same unit object, and then you simply use the braiding to define the interchange law. So remember, the interchange law mixes the two operations in the two possible ways. But in this case, the two operations are the same. So when you're fishing for an interchange law, you need a map from this to that. So you simply exchange the two middle factors. This is something that in general we cannot do, because in general we have two different operations. So in the general case, you don't have anything available to switch B and C and jump from the left to the right. But if you're starting from a braided monoidal category, you have this option. And in fact, everything works, and one gets a duoidal category. There is a converse to this that can be traced back to Schwayal Street. They didn't formulate it in the language of duoidal categories because they haven't been defined, but essentially all the ingredients are present in the paper by Schwayal and Street on braided monoidal categories, so that this can be formulated now in this manner. Namely, if you have a duoidal category in which all the structure maps are invertible, meaning the interchange law is invertible, and the unit maps that I briefly mentioned at the beginning are invertible too, then it happens that the interchange law must be of this form for some braiding beta. And the two monoidal operations must agree, and so you end up with a braided monoidal category. So braided monoidal categories then are a special case of duoidal categories from this perspective. All right? So certain things that can be done in the setting of braided monoidal categories, we're going to do in the larger setting of duoidal categories. But one last example that is interesting and that I haven't seen. So this comes from our work with Javier. Is this category, the category of cosimplicial modules. So I need some familiarity here with simplicial objects or cosimplicial objects. So remember, a simplicial object is a sequence of objects, so in this case k modules indexed by the natural numbers, so x0, x1, x2, and so on. And there are maps linking consecutive terms in this sequence. So from x1 to x2 and back, and so on. There's a collection of maps from each degree to the next and back, satisfying certain axioms. We don't need to go over those in detail. There is a very familiar structure, monoidal structure on this category, which is again diagonal like this, where component of degree n is simply the tensor product over little k of the two components of degree n. That's a familiar thing. There is a natural way of endowing this collection with these two collections of maps, the I and Sj, the faces and degeneracies, or co-faces and co-degeneracies. But it turns out that there is another monoidal structure that is akin to the Cauchy product. This is again like the Hadamard product that we had before. If you attempt to do something like the Cauchy product, so you consider this convolution, there is no natural way of defining here cofaces and codegeneracies. You end up with too many cofaces and too many degeneracies. However, if you do this funny thing of co-equalizing, now if you read this carefully, what's really going on is this. I'm starting here from a pair, x, which is of degree I minus 1, and y of degree j. So if I have an x of degree I minus 1, the last of these maps that I can apply to it is di. Okay, because on xn, the di here runs from 0 to n plus 1. That's how things work. So di is the last one. So you push by di x over to xi. So this is now degree I. So this sits in xi tensor yj. Over here, I have something in degree I minus 1, tensor something in degree j plus 1, because I have applied d0 to y. So you see, I'm identifying things in different components of this direct sum. The last map that I can apply to x, and the first map that I can apply to y, and I identify those two. Well, then it turns out that you can turn this into a cosimplicial object, and these two operations interact in the right way. So one gets a duoidal structure, and this plays an important role in our work. Now, this is for the people who work in algebraic topology. You know, they have simplicial sets for breakfast every day. So I think that this must be known to people, that this construction is possible. It cannot be something that nobody has thought about before, but I haven't found it. So if anybody has a hint to give me about where to find this in the literature, I'd be very thankful. All right, so let's go to some, I'm very, very slow, but I'm very much behind. Some general facts about duoidal categories. So start from a duoidal, let's just look here. You start from a duoidal category. You can consider monoids with respect to one of the operations. And here it's important that I consider monoids with respect to the first operation. And what happens is that this inherits the second monoidal structure of C. This category of monoids with respect to the first operation becomes monoidal with respect to the second operation, which means that you can iterate and you can again consider monoids in here or comonoids in here. And that gives rise to the notion of duoid. So this would be an object of C with two multiplications. And the notion of bimonoid. This would be an object of C with a monoid structure for the first operation and a comonoid structure for the second operation. You can run the other way around. So you can consider the category of comonoids with respect to the second operation, and this category will be monoidal with respect to the first operation. So you can consider monoids and comonoids. There is a coincidence here that comonoids in this category are the same as monoids in that category. So one ends up with three new categories: the categories of duoids, bimonoids, and coduoids. These are familiar facts when one starts from a braided monoidal category. But this is more general, because as we saw before, duoidal categories generalize braided monoidal categories. So these familiar facts from braided monoidal categories, the fact that one has the notion of bimonoid, and that it can be seen in two ways, as comonoids in monoids or as monoids in comonoids, continues to hold. But it is important to point out then that we have these two new categories, duoids and coduoids. So why don't we see those in the setting, in the case of braided monoidal categories? Well, we don't see them because of the Ekman-Hilton argument. But in this new level, these are new things that have a right to exist. So, okay, a quick look at what a bimonoid is. This is what the compatibility axiom now looks like when one unpacks that definition that I gave before. It's the usual axiom for a bialgebra, except that here, instead of using the braiding, one has to use the interchange law. Okay, but otherwise it's the same story as always. The axiom that we learn when we are very little and we are taking a class on Hopf algebras with my mathematical father, Walter Ferrer, who's sitting here. So many years ago, regretfully. Now, there is also the notion of duoid. So what is the axiom for a duoid? Well, very much the same. It's just that instead of coproducts, we have two products. So we have mu as before, but we have this nu mapping the other way around. And that's what the axiom looks like, okay? And of course, there is then the notion of coduoid, which will be dual to the notion of duoid. So what are these strange things, these duoids? Well, okay, so just very quickly, since I went over examples of duoidal categories, what are bimonoids in those? Of course, in the braided monoidal case, a bimonoid is the usual thing that we all know, a bialgebra. In the category of n-graded modules that I gave, that notion was defined directly by hand by Turayev in a series of papers. Okay? So it doesn't matter, he defined it by hand, but it coincides with what we get in this manner. And in the category of R bimodules, what one gets is bialgebroids. Bialgebroids over a commutative base. The more interesting case of bialgebroids over a non-commutative base is more complicated, and it doesn't fit in this language, at least not in this manner. But people like Gabriela Bohm and Gomez Torresillas have done work in that direction. Okay, so examples. All right, what about duoids? I'm not giving examples of duoids. They're harder to come by with, but they do exist. But if one is interested in duoids in the special case of braided monoidal categories, then what happens, of course, is that a duoid becomes just a commutative monoid. So again, we have a version of the Ekman-Hilton argument. I guess this comes from my work with Swamnil, although it's not hard to prove. But anyway, yeah, this comes from my work with Swamnil Mahashan. That one has this version of Ekman-Hilton. In a braided monoidal category, duoids coincide with commutative monoids. So you see, it's like the Ekman-Hilton argument I had at the beginning. At the beginning, we were working with the category of sets under Cartesian product. But this is more general. So if we're working in braided monoidal categories, then duoids are nothing but commutative monoids. Now, what about more general duoidal categories? Does this continue to hold in some form? Well, if you're in a general duoidal category, you have no notion of commutativity because you have no braiding. So you cannot make sense of the notion of commutativity. So you cannot expect this to be true in the same manner. Also, you cannot expect the two monoid structures to be the same because they are with respect to different monoidal structures. So the two operations have different domains. M diamond M, M star M. They're not the same thing. So this doesn't make sense either. So this cannot hold. Thank you. This cannot hold in this manner. However, there is something that can be done, that can be said. And here we're following really good work by Richard Gardner and Ignacio Lopez Franco. Ignacio is my mathematical sibling. We're both children of Walter. So they define two transformations, sigma and tau, in any duoidal category. I'm doing a little variant of what they did, but essentially this is it. So using the unit objects, J and K, one can play around with the unit objects and the interchange law in this manner, and one ends up with maps like this. But I want you to consider this in the case when we're dealing with a braided monoidal category. What is it we're doing in that case? The operations are the same in that case, and here what I'm doing is braiding the middle. We're here using the unit objects outside, and then braiding the middle. So in the case of braided monoidal categories, this canonical map is the identity, and this canonical map is the braiding. You can think of these two maps as substitutes for the identity and the braiding. This makes sense in general duoidal categories. This is the special case of braided monoidal categories. And these maps are very special, and this is really what Gardner and Lopez Franco do. They consider the case of normal duoidal categories. We call them normal when the two units are the same. In that case, the maps sigma and tau look like this. You see, this is intermediate. This normal case is intermediate between the case of braided duoidal categories and the general case of duoidal categories. And in that case, these maps are very special. They go from one operation to the other, and this one also involves a switch change in order. And they prove this result, which can be seen as a more general version of the Ekman-Hilton argument still. Namely, if you have a duoid in a normal duoidal category, then something very special happens. One operation is determined by the other in two ways. So either by sigma or by tau. Thanks, Bas. So what this says, well, So in the case of a braided monoidal category, this recovers Ekman-Hilton because sigma is the identity and tau is the braiding. So this one says that the operations coincide, this triangle, and this one says that it also coincides with the opposite operation, so the reverse operation, so the operations are commutative. Okay, so I need to finish. So I have to skip a bunch of stuff. And just let me look at this picture and try to say something here and finish. I wanted to combine some of these considerations and others that I didn't get to cover to get to that application I had at the beginning, which was about Hochschild cohomology. So the idea was to do the following, to view the Hochschild chain functor, the Hochschild chain complex, as a functor from the category of bimodules, because the input here has to be an H bimodule, to the category of chain complexes. All right, this category is duoidal because I'm starting from C, which is a duoidal category, and the structure is inherited here. This one is braided monoidal. So the idea was, well, I'm going to input here a duoid, and we're going to try to prove that this functor preserves duoids. So it has the right properties, so that it preserves duoids. Those functors are called duoidal functors. So I'm going to apply the functor and get another duoid, but a duoid in a braided monoidal category by Ekman-Hilton is a commutative monoid. So that would explain the commutativity of the product in the Hochschild chain complex. There are problems with this. The operation, the cup product, is defined on cochains, but it is commutative only at the level of cohomology, not at the level of cochains. So this cannot work as claimed, and it doesn't. However, we can understand how it fails and exactly what works, and that was the main point of my talk. But I'm not covering clearly because I don't have any more time. But let me just say that this functor factors through the category of cosimplicial objects. This functor is duoidal, so it has all the right properties, so it would send a duoid to a duoid. And this category is normal, so we can apply here the result of Gardner and Lopez-Franco. So already we have some kind of commutativity at the cosimplicial level. And if we want to go all the way to chain complexes, then we have to analyze this functor. And this functor is not duoidal, but it has some special properties related to the conditions of Gardner and Lopez-Franco. And that's what allows us in the end to deduce commutativity up to homotopy of the cup product on the chain complex functor. This is the end and the references. Our work is not cited here, it's still being written, it's here. And the most important works in relation to this talk are these. So thank you very much for your attention.
There is any question or remarks?
Okay, so I think this is still an open question. You mentioned in a braided monoidal category, so bimonoid is a bialgebra.
Yeah.
What do you need in order to have something appropriate that can be called a Hopf monoid? Is there some...
In a duoidal category? Yeah, that's not... The notion of antipode in the duoidal setting doesn't seem to have a good meaning. Again, the person who has looked at that is Gabriela.
I know. I discussed it with her.
Right. So there are things, if you if you forget about antipodes and try to look at the fusion maps of, the other way of defining Hopf monoids Hopf algebras in terms of fusion maps, just work in that direction.
So, but I think there are situations where you can do it. So at a certain moment with Joost Verkruijsen and Eliezer Battista, we introduced Hopf categories. And there was an interpretation in terms of duoidal categories, and there you have an antipode. So.
Yes. Also, in the case of Turayev, there is a notion of antipode. So there are particular cases in which a notion of antipode still seems to make sense. But I don't know what the right setting.
What the right setting in general is, yes.
Yeah. So that's an interesting thing, yes.
I think Gabriela has a paper
Yes, Gabriela has a paper about this. I don't know that there is a definite answer, but there is. Yeah. Yeah, absolutely. Yeah. That's what I'm. The fusion maps. Yeah, that's what I mentioned. My first answer. Yeah, the fusion maps. Any other question on the map?
Thank you very much for such a nice presentation. I have a question about the example with the monoid graded. Do you put any restriction on the size of the monoid?
No.
So
No,
it
no.
can be uncountable.
Yes, the direct sum there can be an infinite direct sum. So where are we? Yeah. So here, this decomposition, there may be infinitely many pairs, given n, infinitely many pairs are multiplied to n, but the direct sum makes sense. So there are no restrictions. Yeah.
Okay, thank you.
Any other question? No? If not, let's thank the speaker.
Thank you.
Coffee break. Involved by Christian Long, and he will talk on locally finite dimensional representation over some Euclidean format.
Many thanks, Blas. First of all, I have to thank the organizers for organizing this conference, and especially here in Italy, which gives me, I think, my first reason to come here academically. Before, as a good German, you travel as a tourist. And yeah, I'm very happy to be here. It's very nice, and so far everything went very smooth. So my talk is based on a joint work with Gian Hatipolo, but it's basically split in two parts where I first want to do a kind of survey on certain ring theoretic property, and the second part is basically then this work by Gian and me. This talk might not fit completely in this setup here because it is more about ring theory than about Hopf algebras, but Hopf algebras are rings, so there are certain properties I want to look at. The outline is basically, I remind you of a very fundamental theorem of Matlis about commutative rings and injective hulls of simple modules over Noetherian rings, commutative Noetherian rings. And then basically, these are the keywords here, locally Artinian and locally finite dimensional modules. I will look at what can you say about finiteness conditions on the injective hull of a Noetherian ring. And then I'll go to some Hopf algebras. So, well, Matlis, if you look back, Ekman, Schopf, the paper defining injective modules was in the 50s, going back to work of Baer on abelian groups. And I think probably one of the cornerstones at the beginning was Matlis' paper coming from his PhD thesis in 58, who said that if I take a commutative Noetherian ring and I take a simple module, its injective hull is Artinian. Basically, what you do is you localize your ring by a maximal ideal, you complete it, and then you have what's called Matlis duality. You have this order reversing bijection between the ideals of this complete local ring and the injective hull of the module. Vamos, 10 years later, basically said, okay, if you want this for a commutative ring, then it's basically equivalent to saying that any localized ring, if in the commutative setting, is Noetherian. So the point of this whole talk and of this line of research is to see how much can you say for non-commutative Noetherian rings, and in particular non-commutative Noetherian Hopf algebras. So let's start with some very easy examples, also very old. The first one is Hurstein's example from 1965, which he did not intend to provide as an example for the non-Artinianness of injective modules of simples. But just take this upper triangular matrix ring, take the integers localized by a prime, for instance by 2, and take the fraction field. And this is a nice left Noetherian, but not right Noetherian ring. And if you take here the, okay, they can't see. If you take the upper right corner of this matrix ring, it's simple, obviously, and it sits essentially inside the right column of your upper triangular matrix ring. So essential just means that your module sits very large in it and intersects all other submodules non-trivially. So in particular, you have an extension, an essential extension of a simple cyclic module, even a projective, but the later one is not Artinian, right? So it's a very elementary example. And of course, Hirstein used this example not to provide such an example, but to show that the intersection of the powers of Jacobson radical is not 0. If you have a one-sided Noetherian condition, if you have a two-sided Noetherian condition, this question is still open whether the intersection has to be 0. This is not the point of the talk, but it's a side remark. So, but there are other very nice examples where you see that this property of the injective hull of a simple being Artinian or having some finite condition is rather subtle on some non-commuted rings. So take the first Weyl algebra over some ring. Then there's a nice little paper by Hirano from 2000. He addressed exactly the question, is the injective hull of a simple Artinian or not? And if you take the integers, or more generally, you have a finitely generated Z algebra, then the answer is yes, because basically all the simples are annihilated by some prime number P, and then things boil down to the first Weyl algebra over the field of P elements, which is easy then. But if you take the quotient field of the integers, the rational numbers, then the answer is no. Because first of all, your polynomial ring Qx becomes a simple module just by ordinary formal derivation of polynomials. And inside your injective hull, you have a chain, an infinite descending chain of submodules which are given by localizations of certain monomials once you have an infinite set of elements in Q. So why does it work for Z, why not for Q, right? But if you look at it further, you see that, okay, the injective hull might not be Artinian, but it is locally Artinian in the sense that any finitely generated submodule will be Artinian. And in this first Weyl algebra case, you can give an easy argument. You say, okay, it has Krull dimension 1, and whenever I have a cyclic module which is not isomorphic to my ring, then it must be Artinian, right? And so this first Weyl algebra of the rationals doesn't satisfy this outcome from Mutley's theorem, but you have a local version of this, at least for finitely generated submodules. So replace Artinian by locally Artinian and see what other examples you have, and give it a name. So we couldn't find a better name and just said diamonds. Diamonds are precious, right? So so we say a ring satisfies diamond if the injective hull of all simples are locally Artinian. And floating, over quite general argument is, okay, what can you say? When is a left Noetherian ring? When does it has this diamond property? Well, just take the torsion theory generated by all the simples. The torsion part are exactly the semi-Artinian modules. And if it's closed under taking injective hulls, then you're done. And so this is basically the overview of this diamond property. But of course, if I give you a ring, a Noetherian ring, you won't be able of saying whether this holds or not, unless you dig into the algebra. Yeah, so it's just a rephrasing, basically. But if you're going close to commutativity, like if you have a Noetherian PI algebra, for instance, or if you have a fully bounded Noetherian ring, fully bounded means that any prime factor has the property that any left essential ideal contains a two-sided ideal. So two-sided ideals are plentiful. It contains a non-zero two-sided ideal. then this is, such rings are called fully bounded Noetherian. Of course, I assume they're both sided Noetherian. Then Yad Gonka in 76 showed, yes, it's true. Whenever I take injective hull of a simple and finally generate mod of it, it is Artinian. Okay, let's go back to Weil algebras, and Stafford in 85 showed that, okay, while the first Weil algebra over field is fine because it has Krull dimension 1, once you get to a second Weil algebra or higher, the answer is no. You don't have this finiteness condition on injective hulls. Why is that? Because he invented this element, let's say. So you take, for the nth Weil algebra, so it has two n generators, so it's the iterated first Weil algebra of the n minus first algebra, Weil algebra. You take n minus 1 linearly independent elements over the rationals, and then you form this element. So x1, y1, x until xn, yn are the generators of your Weil algebra. And what he showed was that this element, the single element, generates a principal right ideal which is maximal. Okay? So you have this Weil algebra of Krull dimension, of a GK dimension to n, very nice, and this is a simple module, and it sits inside another cyclic module in such a way that is essential, so it's large in there, but the Krull dimension drops 1, so n minus 1. So starting from n equals 2, it will not be Artinian. Meaning that this is a very ingenious example to find this. And this also shows you the difficulty. You have to find those non-split exact sequences of simple modules and non-Artinian bits that then disproves or proves your condition diamond.
And the first step is multiplication by x1, yeah?
Yes. Yes, exactly. So, exactly, you just map A1 to x1 times A. Yes. And, yeah. So, okay, let me just, this is a kind of survey part, and I will mention some results of Ken Brown that is here, and Paula Carvalho and Jurek Maciuk. So, just play around with this. Let's look at skew polynomial rings and differential operator rings. Let's look at enveloping algebras of Lie algebras. What can you say about this property, this finiteness condition on injective hulls of simples? Paula and Ian Mussen, they showed that, well, if you take the quantum plane, so maybe the easiest and nicest non-commutative example, to some parameter q, then it has this finiteness condition on your injective hulls, precisely if the parameter is a root of unity. So the difficult part here is to prove that if it's not a root of unity, you find this exact sequence with a simple and so on. And it looks in a way very similar to the example I had shown you in Stafford's thing. Then there's a series of 3 papers by Ken Brown, Paula Carvalho, Jurek Maciuk, which basically deal with the situation very nicely and have obtained very deep results. So in 2019, they said, they proved that if you start with a commutative affine algebra with some field, then and take some automorphism of R and form the skew polynomial ring, then this skew polynomial ring satisfies this property diamond precisely if all the simples are finite dimensional. Okay, that's still an if and only if, and you might say, okay, when does this happen? You might conjecture, okay, this happens only if the automorphism has finite order, and they gave examples showing that there are examples of automorphism of infinite order, such that all the simples are nevertheless finite dimensional. So a very nice result, and as I said, there are 3 papers. Mathematische Zeitschrift, Journal of Pure and Applied, and this is still ongoing in the review process, I believe. The second set here, the last statement I put here is to show that this condition is very subtle. So you could take the power series ring over, let's say, the complex, and take any automorphism and form the skew polynomial ring, and it will have this diamond condition. This is a local ring of Krull dimension 1. On the other hand, if I localize my polynomial ring at the variable y, I also get a commutative local ring of Krull dimension 1. But if your automorphism sends y to qy, and q is not a root of unity, then it doesn't have this property. So why does one, well, you can one is completely or not or something, but I think this is quite interesting, and if you're interested, I can just warmly recommend these papers. Okay, just let's see how I'm doing. You can say a bit about differential operator rings, but not much. Just let me say that, well, if you start with a derivation and you form the differential operator ring, if the derivations happen to be local nilpotent and your base ring was commutative and affine, and maybe the field is algebraically closed, then also the differential operator ring has your property. But this branch is not very exploited, I would say. I'm going through these parts here. Let's better go to Hopf algebras and universal enveloping algebras. So there's a very nice example here of the Heisenberg Lie algebra, yeah, a three-dimensional one. If you take just a three-dimensional one, which is nilpotent, then it does satisfy diamond, because you basically have to verify your property diamond on factors modulo maximal ideals from the center in this case. And the center is very nice there, yeah, it's just generated by this Z. And you either have modulo maximal ideal, you have a polynomial ring in two variables, or the first Weyl algebra. But if you take a tensor product of two of these things, or if you like the enveloping algebra of H cross H, then it doesn't, because you have this epimorphic image to the second Weyl algebra. And then you have Stafford's result that says, well, there's always such a short exact sequence where things fail. So what happens here nilpotent? I mean, one is nice, the other one is also nilpotent. What can you say in general? An older result by Ian Musson said that if I take the two-dimensional non-abelian Lie algebra, which is separable, but not, which is solvable, but not nilpotent, then it doesn't satisfy diamond. And using this, John and me, we proved that classified actually when the enveloping algebra of a finite dimensional solvable, but when just nilpotent, actually satisfies this condition. It is either you have an abelian ideal of codimension 1, so you have a very a big part that commutes inside your Lie algebra, or you have a certain, there are two exceptions, let's say 5 and a 6-dimensional Lie algebra, which might occur. You can always, of course, add some abelian factor to it, and it will preserve this property. But you see, it's a strange property. Okay. Now, I want actually to talk about this part with John, where we substituted the question whether the injective hulls are Artinian by, when you are over a field, whether the injective hull of a finite dimensional module is actually locally finite dimensional. So, and I will give some examples showing where this appears in the literature as well. So you start with, your algebra is always affine Noetherian, and I will always assume that the base field is algebraic closed and character is 0. The question here is, when is the category of locally finite dimensional modules closed under taking injective hulls? Yeah, so I take a simple module which happens to be finite dimensional, and I take the injective hull. What can I say? Is any finitely generated submodule also locally finite dimensional? Now, almost trivial examples are certainly simple algebras. If they're infinite dimensional, they don't have finite dimensional representation, so it's cheating. If they are finite dimensional, they are Artinian. But also, if you take a Noetherian PI algebras, then this argument by Z. Conca applies. And so if it's a Noetherian algebra, K algebra, that somehow has some polynomial identity. Non-trivial examples arise here in the 80s by Ian Musson and Stephen Donkin. If you take a polycyclic bifinite group and a field and take any finite dimensional module over the group ring, then Ian Musson showed that if the characteristic is positive, the injective hull of this finite dimensional module is Artinian, and so it's also locally finite dimensional. And in characteristic 0, Steve Donkin proved that, well, you have our property that the injective hull of a finite dimensional is locally finite dimensional. Okay, there are, of course, Hopf algebras, group rings. So what can you say about Lie algebras? So this has been also addressed by Stephen Donkin and Jörg Feldfoss. Stephen Donkin proved that if you have a finite dimensional Lie algebra that is solvable, then the enveloping algebra is essentially closed, meaning that locally finite dimensional modules are closed under taking injective hulls. Jörg Feldfoss proved the converse in a paper in 2006. So here the situation for finite dimensional Lie algebras is completely clear. But of course, they are both Hopf algebras, the group rings, and the enveloping algebras. What can you say here about, well, this is just an example to illustrate something. If I take the enveloping algebra of SL2, semi-simple Lie algebra, then there's a result by Dahlberg who showed that the injective hull of simples are Artinian. But you might have extensions of some one-dimensional simple module and an infinite-dimensional simple module. Yes. So you might have, and it's non-split. So you might have an extension, an essential extension of a one-dimensional module which is not finite-dimensional. Yeah. I mean, if you want concretely, these are usually the generators EFH of SL2. Okay. Now. How can we address this problem in general, although it doesn't help sometimes? Take an algebra, we're always an algebra over field, take the finite dual, this is a co-algebra, I don't have to explain this here, and then you basically check that our property that we wish to hold, namely that injective hulls of finite dimensional modules is finite dimensional, holds precisely if each finite dimensional submodule, or the largest locally finite dimensional submodule of a module V, splits off. And this is also equivalent to saying that the finite dual is actually an injective left A module, where you use that you can identify the category of locally finite dimensional modules with the category of comodules over this finite dual, and you know that, of course, this co-algebra is the injective cogenerator, and so this gives you the overall view of this problem. But again, I gave you an algebra. Can you verify this? You know, this is not clear. So one thing that helps if your prime ideals are nice, if basically if they're completely prime, so if all prime factors are one-dimensional, are domains, and then one-dimensional, since I asked the algebra to be affine and the field to be algebraically closed. In this case, our property can be verified just on the injective hull of those base fields where you twist the multiplication coming from the, well, I need, yeah, this chi. And examples of such cases are, for instance, the quantum Euclidean spaces. So Goodall and Letzter in their monograph in 1994 proved that if you have this quantum Euclidean space, so you have n non-commutative variables, they commute up to some matrix Qij. If the group generated by these elements Qij is torsion-free, then actually you have the hypothesis of this theorem, basically. And going a bit further, finding some sufficient condition for essentially closeness is the following. If you have this property that any co-finite dimensional maximal ideal, so any maximal ideal whose quotient is finite dimensional, contains some ideal Q with some special property, namely it is polynormal, that means it has a series of generators. The first one is normal, meaning that the left and right ideal, principal ideal is the same. And the second one is normal modulo the first, and so on and so on. And if A over Q, well, has the property you wish for, then you basically have also that your algebra is essentially closed. The second one, the second property, you might also have in some cases that your algebra Q that sits in your maximal ideal of final codimension has the Artin-Ries property, and A over Q is pi. So this looks very strong, but in some applications this holds. And then you can just go again to this quantum Euclidean space example and also rule out the case where the parameters do not generate a torsion-free group. Okay, but OR extensions, as I mentioned this before, and I said this was how many minutes? 1 more minute? 7. Okay, I thought it was less. Okay, so for the OR extension case, it looks much nicer than in this property I told you about before, this diamond property. Basically because, well, if you start with a commutative ground ring, basically because we have these, we can verify these sufficient conditions I mentioned here before. And for instance, here take any automorphism and form the skew group ring or any derivation. They always have this essential closeness once your base ring is commutative affine. The mixed case we just could verify if we assume also R is a commutative Hopf algebra. I don't know in general if not, if it's how to address this in general here. Okay, the arguments use classical ring theory, like going to the Ries ring of a certain ideal and using arguments by Bell and Goodall. So, going to Hopf algebras, the final part of my talk. We have seen already 2 Hopf algebras being addressed. So, for instance, the group ring of a polycyclic bifinite group and the enveloping algebra. So what can you say in general about Noetherian Hopf algebras? When do they have this property? And the first thing is you can pin it down to the trivial representation. Once you have a bijective antipode, you can verify it. You have this kind of isomorphism for finite dimensional modules V and some module you like U. This is actually a functorial in U. And then you see that the tensor product of the injective hull of the trivial representation tensor with this any finite dimensional module, this Hom functor, Hom blank EK tensor V, is a composition of these 2 functors, namely the Hom H EK functor blank EK, and inside you have the tensoring with the dual over K, and so which is exact. So you have that this guy is always an injective H module, and then your injective hull of this finite dimensional module embeds into that injective module. And then what you basically just need to know is whether the injective hull of the simple is locally finite dimensional. That's all. But nevertheless, you can say, well, I'm just reduce it to one simple that I have to check. This comes with the augmentation map, and it has a nice kernel, the augmentation ideal. And if this augmentation ideal has good properties, the properties I just mentioned, then of course you can put 1 and 1 together and prove that those Hopf algebras satisfy the condition that locally finite dimensional modules are closed under injective hulls. Okay. Then we went to some classification results. Here's one, Goodall and Zhang, 2010. They looked at Hopf algebras of GK of low GK dimension. If you start with a Hopf algebra that's a domain and satisfies that the GK dimension is 2, and you have this homological condition there that there are self-extensions of K and K, then this Hopf algebra is Noetherian if and only if it fits into one of these list of Hopf algebras where I was here sloppy and didn't tell you exactly which are these certain Hopf subalgebras. But, and then we just went through this list and said, okay, they all have our property, but of course we are far from saying in general which Noetherian Hopf algebras have this property that locally finite dimensional modules are closed under injective hulls. We can, however, recover, for instance, Donkin's argument once you have a Hopf algebra which is a cross product of some commutative Hopf algebra and some Noetherian Hopf algebra whose augmentation ideal, R plus, has a nice Ries ring, as I mentioned before. If this happens, then we can also prove in the same way that locally finite dimensional modules are closed under taking injective hulls. And this, of course, applies to solvable Lie algebras, because there you have a unique maximum in the potent ideal, and this will be abelian, so this is a commutative Hopf algebra, and that the augmentation ideal of this U of H has an Adheron Rees ring is a result by someone called Pickel from 1972. And that's it. Thank you very much.
Question or remarks? Okay, no.
What happens with the
Q of SL2. UQ. I don't know. I should have looked at it, yes. But I don't know. Yeah.
I think both properties fail if Q is not under infinity and hold if it is under infinity. They hold because it's PI and it's under infinity. And fail because trivial module, all finite dimensional extensions of it are semi-simple, but
Oh, yeah.
but it's the injective hull is infinite dimension.
Yeah.
Any other question? No, that's the English speaker. Next speaker will be Daiki Shibata, and he will talk about semi-simple Hopf algebra low dimension.
Thank you for your kind introduction. And I'd like to thank the organizers to be here and give a talk here and about this. Okay, this is based on sorry? Here, okay. This work is ongoing joint work with Kenichi and my PhD co-student Ryota Wakao. Okay, last year we have classified pointed Hopf superalgebra of low dimension. So today we are focused on the semi-simple case, and we will give a classification of all Hopf superalgebra of dimension up to 10. Okay, so to begin with, let us recall the definition of Hopf superalgebra. Okay. In this talk, we walk over an algebraic closed field of characteristic 0, and I denote this board K. And Z2 is the group of order 2. Okay, the category of KZ2 comodules, which I denote S-spec, has become a symmetric tensor category with this non-trivial flip. Okay, and inside of this category, a Hopf superalgebra is an Hopf algebra object in this category. Okay? This is the definition of a Hopf superalgebra. Okay? And we say that H is purely even if the odd part of H is trivial. Okay? So such purely even object is not really Hopf superalgebra, just the ordinary one. Okay? So typical examples are here. The first one is the exterior algebra, of course, and the second is enveloping superalgebra of Lie superalgebra G. Okay, and using a PPW-like theorem, we can decompose like this as a super coalgebra. Okay, so as in the non-super situation, Constant shows that for a super commutative Hopf algebra H, then such H decomposed can be replaced the semi-direct product of group algebra and enveloping algebra of Lie superalgebra. Okay, so if H is finite dimensional, then H can be written in this form. Okay, so in the classification theory, such called a supergroup, such supergroup is somehow a trivial one. Okay. Recently, Andrews Kubich, Tingoff, and Gelaki given a one-to-one correspondence between these two sets. The upper one is consisting of Hopf algebra with a group-like element of order 2. Then they construct a Hopf superalgebra. Here I denote AU. Here AU is, as an algebra, the algebra structure of AU is unchanged, and its parity is given by this formula. And the coproduct is somehow very, complicated. But yeah, this is the coproduct of AU. And then we can make this AU into a Hopf superalgebra. Then, of course, if you take a group algebra with a group-like element of order 2, then you can construct non-trivial Hopf superalgebra like this. Okay, very recently, Soe and McLaughlin classified Hopf algebras with such that its odd part is non-trivial of the dimension up to 4, like this. So today, our main result is this. We have classified Hopf superalgebra H of the dimension up to 10, okay, including their result. Okay, so what is our method? Our method is quite simple. Okay, SPEC is just a comodule over KZ2, and we can embed this category into Yetta-Drinfeld modules over KZ2. Okay. And using bosonization technique, then we can find a Hopf algebra. We can find an ordinary Hopf algebra inside this. So we use the inverse procedure of this. Okay. So if you have an ordinary Hopf algebra A here, then we can, we can find a superform inside of that. Okay. I mean, we give a criteria for this Hopf algebra to be a Hopf algebra object inside here, and moreover, we give a criteria to be such object inside here. Okay. This is my method, our method. Okay. Okay. You may ask why you choose 10. Why you choose 10? One reason is we have 10 fingers. No way. Okay. Yeah. This is the reason. Because the classification of Hopf algebra, ordinary Hopf algebra of up to of dimension up to 12 has been done by many Hopf algebraists here. So we use their results and find superforms inside of that. Okay. Okay. Let's play super classification. So first of all, we introduced what is bosonization. Bosonization is for a super algebra H. Then we can make this H hat into an ordinary Hopf algebra using these formulas. Okay. The formula is quite terrible, horrible thing. But please remark that there are 3 properties of this. First one is if H1, the odd part of H is non-trivial, then H hat is neither commutative nor co-commutative. Okay? And the second one is representation category are the same. The third one is the group-like element of H hat decompose into the group-like element of H0 part and C2. Here C2 is the multiplicative group of order 2. Okay, so we know that. So using this property, we know that H is semi-simple or pointed or spherical Shibari means a Shibari property that has a Shibari property, then so is H hat. This is equivalence. So if you want to classify semi-simple Hopf superalgebra, then you should, you should know the semi-simple Hopf algebra.
In which sense are the representations categories the same?
Number
Number two.
two, this means here is the representation category of Hopf superalgebra means the super vector spaces endowed with algebras.
So on one side you have super vector spaces to begin with.
Exactly, yes. Okay. So this is immediate consequence of the bosonization. This says any Hopf superalgebra of odd prime dimension should be purely even. Okay, the proof is quite simple because let H be a such Hopf superalgebra, then its bosonization, the dimension of bosonization is twice of P. So using the N's classification results, then such H hat must be trivial Hopf algebra. I mean group algebra or H0. So the H1 should be 0. So it's quite simple, I think. Okay. So by Rutherford's bosonization technique, then there is a one-to-one correspondence between Hopf algebra object in the Dirichlet category and Hopf algebra having a split, having a projection and injection, satisfying this condition. And since we are in, since the base Hopf algebra is KC2, so we can, interpret this pi under iota into in the language of group-like elements like this here. So if we set AD, I shall call admissible data for A, then there is a one-to-one correspondence between the Hopf algebra object in the Dirichlet category whose bosonization is A and AD. So we get this one-to-one correspondence. So we just focus on AD. What is AD? Okay. So before that, I explained the converse, how to get a Hopf algebra object in Dirichlet category. So let A be a finite dimensional Hopf algebra and take a G and alpha of the inside of ADA and denote the pi to be the corresponding projection. Then the pi coinvariant subalgebra, I denote A co-pi, becomes a Hopf algebra object. Yeah. The algebra structure unchanged, but co-algebra structure is, is given by this formula. Okay. Now, since the Dirichlet category is strictly bigger than S-spec, so we have to know when this object belongs to S-spec. Okay. Before that, we decompose this H into this weight space given by this formula because we have two action. Okay. So this is a pi action and this is a G action here. So we get if H belongs to S-spec, if and only if this off-diagonal part should be 0. Right? So this is a condition. And we write down in terms of G and alpha. Then we get this proposition. Okay? So in this case, we get a Z2 gradation given by this. So if H is purely even, if H is purely even, if and only if G is central. So we introduce this notion as super data for A. If G satisfy G is not central and satisfying this condition. Okay. So in this way, we get one-to-one correspondence between SDA and non-trivial Hopf superalgebras.
G has order 2 here, yeah?
G is, yes, exactly. Order 1 or 2. So, let me explain. Let me explain our classification method. Let A be a finite dimensional non-trivial Hopf algebra with whose group-like elements are split into this formula. And its dual, the group-like element of its dual, also split into the C2. So how to find a Hopf algebra satisfying the odd part is non-trivial and whose Bostonization is equal to A, given A. So there is 2 steps. One step is compute SD superdata. Recall that SD is given by this relation. Okay, and determine the representatives of SDA. Yeah. So we want to determine SDA here. We have to know the Hopf automorphism or Hopf automorphism, but yeah, we can't do it. So if SDA is empty, then there is no such H. Okay, the step 2 is determine the structure of co-pi. This is a little bit hard step, but we can do in principle. Yeah. Okay. Using these steps, then we get Hopf superalgebra, non-trivial Hopf superalgebra, whose Bostonization is equal to given A. So let P be an odd prime. Let me see an example. Let me show the examples. Let P be an odd prime, then the P square dimensional Hopf superalgebra must be purely even. Okay? The proof is based on many results of Hopf algebraists. First, we know that twice of P square Hopf algebra is isomorphic to one of these guys. If A is semi-simple, then that should be isomorphic to B0 and B0 dual. I shall not give a definition here. Then, if pointed, then such guy should be coincide with these 4 ones. Using so calculated directly, then we get SDA is empty for any such Hopf algebras. Okay. The next one is if H has a dimension of twice of P, then and if H is semi-simple, then H should isomorphic to the group algebra of the dihedral group with twisting. Here, twisting means AEG construction. And if H is pointed, then such guy should isomorphic to ACPD. I shall give the definition in the next slide. This is a kind of superversion of quantum linear space. So the proof is essentially the same as this. Just use our best knowledge. Okay. Since semi-simple Hopf algebra of dimension 4 times P has been done by the classification of such guy done by Natale, and such semi-simple Hopf superalgebra is isomorphic to A. L is a parameter, and if L is not 0, then we show that SD is empty, and if A 0, then there is just one superdata. And on the other hand, we know that this is a non-trivial Hopf superalgebra, so just these should coincide. Okay? So what is ACP? Let me give a definition of ACP. Okay, let gamma be a finite abelian group and take a natural number theta, and D consists of these data, G, chi, mu, and epsilon. Okay, satisfying these, these compatible relations. Okay, okay. And A gamma D is defined by this formula. As a superalgebra, this guy is generated by gamma and zeta 1 and zeta 2 and zeta c, satisfying this situation. And this A gamma D becomes a pointed Hopf superalgebra with this structure, skew primitive one. So, okay, this is the definition of A gamma D. Okay, so okay, so we know that by our classification results I explained before, then we get if the dimension is 3, 5, 7 is prime number, so there is no such Hopf superalgebra, and 6, 10 is the last proposition. So open is 4 and 8, 4 and 8 cases. Okay. So in ordinary Hopf algebra cases, the non-trivial Hopf algebra A of dimension 8 or 16 is isomorphically one of these four Hopf algebras. For example, if A is dimension 8 and semi-simple, then that one isomorphic to A8, the Masaoka and Katz-Papazian Hopf algebras. Okay, so we want to find a superform of these guys. Okay, so first, as a pointed case, since these are generated by degree 1, so this guy, this guy is generated by group-like elements and skew primitive elements, so we can find its superform quite easily, easier than semi-simple case. So this is the result. So if let H be a pointed Hopf superalgebra of dimension 4 or 8, then such guy is isomorphic to A gamma D. I give him the before slide, and this is the result. Okay, so the pointed case is done. So next, semi-simple case. Okay, semi-simple, non-trivial semi-simple Hopf algebra of dimension 8 or 16 have been already classified Masaoka and Cassina. And according to their results, such guy isomorphic to one of these A8 or HD-11 or HB1 or something like that. I follow Cassina's notation here. Okay. Then one can easily see that the superdata is empty if A is black Hopf algebras. Okay. So we just focus on red Hopf algebras. Okay. Okay, because our target red Hopf algebras can be realized as invariant extension of the form like this. So here G is one of C2-2 or C2-3, C4 times C2, and F is always C2. And with trivial right action here. For example, Masaoka A8, then the left action and cocycle, dual cocycle is given by these formulas. So in principle, we can give an explicit description of SDA. A is an invariant extension in terms of group G and F, of course. And this is a very special thing. Our target A here, A8 or D something. Our target writing the superform A down is how to say, relatively easy because it's a group-like element inside of GKG sharp 1. In general, this should be this might be a T here, T is here, but in these cases, we can show that this contained in here. So thanks to this fact, we can write down this co-invariant space in how to say explicitly. So I write down this space explicitly and obtain a new series of semi-simple Hopf algebra, which I denote A H gamma of D. So I give it the definition of H gamma. What is H gamma D? Gamma is a finite group, not necessarily abelian. And take D to the data T, P consisting of T, P, lambda, and mu, consisting of this data. T is an inversion of gamma, and P is a homomorphism compatible with the given T, and lambda is a map satisfying this condition, and mu is normalized two cocycle on gamma. And I assume that this gamma, these conditions satisfy this compatible relation, and set H gamma D to be the superspace of this form. Then we can show that this H gamma D is semi-simple Hopf superalgebra whose structure is given by this formula. Maybe the coalgebra structure is well known that, but the algebra structure we use T, an inversion T, and this is maybe non-trivial thing. Okay. Okay. As an ordinary algebra, the dual of group algebra K gamma is isomorphic to the zero part of this guy, and moreover, once we can see the group-like element inside of H gamma D coincide with this guy. Okay, so this is classification results. Semi-simple Hopf algebra, Hopf superalgebra of dimension 4 or 8 is isomorphic to one of this. Is isomorphic to H gamma D. Here gamma is given by this one, and D is given by this one. And also we determine its dual explicitly. Okay. Oh. Yeah, this is our result. Okay, so the semi-simple case also done. Okay. So the last one is Chevalier property, Chevalier 1. Okay. Okay. So let me define a Hopf superalgebra having a super property of dimension maybe 8. Yeah. Okay. First, we take a fourth root of unity I, and take epsilon eta to be 0 or 1, and let K8 plus minus epsilon eta denote the 8-dimensional superalgebra generated by these guys. And here the blue means odd generator, and black means even generator, satisfying this relation. And then this guy becomes a Hopf superalgebra by letting this co-multiplication and the co-units and both here. So please note that since this S of W is equal to I W, so S fourth power of S is identity, but S squared is not identity. So in particular, we have this is non-semi-simple. Sorry. So whose bosonization is isomorphic to H16 something. Okay. So thanks to this isomorphism, we get this K8 plus minus is non-semi-simple, and this guy has a Chevalier property, and this guy and its dual is not is pointed, not pointed. Okay. Okay. Oh, this is my our classification results. So any Hopf superalgebra with non-trivial odd part of dimension up to 10 is isomorphic to one of these, how to say, these guys. Okay. Okay. I shall stop here. Thank you for your kind attention.
And then in question, Max?
Yes.
So I think he could add 11 instead of 10.
11, yes, exactly. Yes, yes, exactly. Yeah. Because it's still open. Yeah, I know that. Yes. Thank you so much. Thank you so much.
Want the microphone?
Thank you.
Since we have time.
Then let's continue with the next talk. Our last talk this morning will be by Paulo Sarocco, and will be, everybody knows what the normal Gabi algebra is.
At least by the end of the talk, I hope. Thanks, Blas. Thanks to all of you for being here. I'm well aware this is the last talk of the morning. I will try to keep it as painless as possible. And well, thanks to the organizers for giving me the opportunity of speaking here today. Now, what I would like to present to you are this notion of Gabi algebras that we recently introduced with Jos Verkroijs and Johannes Berger, and that follows a discussion with Gabi Bohm, that you might know as Gabriela Bohm, and well, was recently published in Advances. Now, the idea of Gabi algebras is that they arise from a different perspective on the Tannakian formalism. In the Tannakian formalism, I will recall it in a moment, we focus on the monoidal structure. For getting Gabi algebras, we focus on the closed structure. Now, let's just recall briefly. I thank all the speakers that already recalled whatever I need about Tannakian formalism. So if we have a field, then we have the category of vector spaces, and we have an algebra, then we can consider its category of modules. This comes together with a forgetful functor to vector spaces. If we are interested in recovering the algebra, this can be seen as the algebra of natural transformations from the forgetful functor to itself. But the important point for us is that the more structure we put on the algebra, the more structure we get on the category of modules. So we have already seen that if we're working with a bialgebra, then we have a monoidal structure lifted along the forgetful functor. Vice versa, if we have monoidal structure lifted along the forgetful functor, we can reconstruct the bialgebra structure, and we can even claim that we have a bijective correspondence between monoidal structures and bialgebra structures. Now, if we want to push this forward, then whenever we have a bialgebra, we always have that the category of modules is left and right closed. By this, I mean that tensoring on the left and tensoring on the right always have a right adjoint. We know also that liftings of the right closed structure correspond to Hopf algebra structures on the bialgebra. And this is fairly easy to see because we said we already have a closed structure, so we already have a right adjoint on tensoring on the right. Now we are saying, okay, we have a second one. They need to be isomorphic because they are adjoints of the same functor. We adjust a little bit the second one, and we realize that the candidate isomorphism is induced by the Hopf-Galois map. And then we know that this is an isomorphism if and only if the Hopf-Galois map is invertible, if and only if we have an antipode. Going even farther, lifting the biclosed structure, so both left and right closedness, now corresponds to having a Hopf algebra with bijective antipode. The trick is the same. We already have one adjoint. We are saying we have another one. They need to be isomorphic. We're just one of the two. And then we have that the bijectivity of the expected map is equivalent to the bijectivity of this twisted Hopf-Galois map, which corresponds to an op antipode. Having an antipode and an op antipode means that we have an invertible antipode. And this is more or less the core of Tannakian formalism in a certain sense. And now the point is, in order to perform this, we always first consider the monoidal structure and then the closed monoidal structure. But since the 60s, since Eilenberg and Kelly, we know that closed structures have a dignity which is almost equivalent to the one of monoidal structures. So what can we say if we only would like to lift the closed structure without considering the monoidal one? Now, to answer the question, let's proceed step by step. Let's start one step far away from where we want to go. So let's start with skew monoidal structures. These are morally monoidal structures where we do not ask the constraint to be invertible. So they also go in weird directions, like the right one doesn't go in the direction one would expect. But this is the fair definition of a skew monoidal category. The constraints are subject to 5 commutative diagrams and not just 3. But then we can wonder what happens if we ask the constraint to be invertible. Then we call the skew monoidal category to be right normal if the right unit, left normal if the left unit, associative normal if the associativity constraint are invertible. All together gives the definition of a monoidal category we're familiar with. Now, on the other side of the medal, we have skew closed categories. These are categories together with a distinguished object that plays the role of the unit, a bifunctor that plays the role of an internal home. And just to have in mind a toy example, consider an K-algebra, not necessarily commutative, left modules over the K-algebra, and K-linear maps between left modules with regular right action on the V. So we have this data, and we have the constraints that reflect more or less the left, right, and unit constraint, which are given by a map I, which morally evaluates the identity. We have another map J, which morally picks the identity. And then we have a natural transformation, natural in the lower indices, denatural in the upper index, gamma, which is morally the counterpart of associativity, and they are subject to 5 commutative diagrams we don't care at present. But the point is that you should think about gamma as post-composing by a map. We start with a K-linear map, we pick a K-linear map, we get the composition. Now, as we have monoidal functors, we also have closed functors between closed categories. They respect the unit, respect internal homes, and are compatible with the coherence transformations. And, well, as we have normality for monoidal structures, we also have normality for closed structures. The first one is fairly expected. Right normality means asking I to be a natural isomorphism. But now a second of thought on the examples, on our toy example, already reveals that asking J or gamma to be invertible is completely pointless. In fact, left normality corresponds to the invertibility of a function that depends on J. Associative normality corresponds to the bijectivity of a function that depends on gamma. And the 3 together give the definition of a closed category. Now, they might look like weird, but they are exactly the other face of the medal in the following sense. If we have a category with a distinguished object, a tensor product, and an internal home, then skew monoidal structures on the tensor product are in bijective correspondence with skew closed structures on the internal home. And the monoidal structure is left, right, or associative normal if and only if the corresponding skew closed structure is left, right, or associative normal. And just for the sake of simplicity, if we are in this nice setting with adjunction, then the associative normality can be rewritten in terms of the bijectivity of this morphism in the category. So this does not go outside of the category as it was happening before. So now that we have the setting, let us try to answer the question starting from a more general framework. So instead of directly looking at K-algebras, let's look at skew closed categories and monads. We have C, skew closed, nothing more. We have a monad on C, then we can consider the Eilenberg-Moore category. We have a forgetful functor. What does it take to lift the skew closed structure? Answer, this lifts if and only if the distinguished object is an algebra. Okay. We have a natural transformation S, which is the one that allows us to make the internal home an algebra for the monad. And they are required to satisfy 5 properties. The first 2 properties are telling to us that the algebra structure induced by S is indeed an algebra structure, so the internal home is a T algebra. The last three properties are telling us that I, J, and gamma are morphisms of T algebras. So nothing surprising. What about the monoidal setting? Let's do one step toward our aim. We have a skew closed monoidal category, well, a closed monoidal category, so we can speak about monoids therein. We have monoids, so we have the monad induced by tensoring by the monoid. We have the Eilenberg-Moore categories, the category of modules. Then the skew closed part, so not the normality conditions, only the skew closed part lifts if and only if, well, the algebra is augmented. And we have a family of natural we have a natural transformation, so a family of morphisms, natural in X and Y, which is the mate of the S under the adjunction, which satisfy the analog properties. So the first two are those that ensures the internal home as a module. The last three, that IJ and gamma, are A-linear maps. And finally, let's go to the K-linear setting. Let's see how we can translate this for a K-algebra. Then we have that the structure lifts to modules over a K-algebra if and only if the algebra is augmented. And we have an algebra map delta, which we evocatively denoted with A plus A minus, if you're familiar with right and left bialgebroids, which satisfy these three properties. And if this is the case, then the module structure on the K-linear maps is given by A plus outside, A minus inside. And now we decided to call this a Gabi algebra, which might suggest general associative bialgebras, or I leave to your imagination the other possibilities. But we need examples. Do these Gabi algebras exist? I know somebody in the audience will complain. My first example is, of course, Hopf algebras. If Hopf algebras are not an example, what's the point? So if we plug the antipode on the second leg of the co-multiplication, then this gives the A plus A minus, H plus H minus we were interested in, and this is familiar to us. Another family of examples, a little bit more surprising, are one-sided Hopf algebras in the sense of Green, Nichols, and Taft. These are bialgebras whose identity only has a one-sided convolution inverse. In particular, if we consider those that have a right convolution inverse, so we have a right antipode, then plugging the right antipode on the second leg gives a Gabi algebra. And this is an example in which we are lifting the skew closed structure from vector spaces, but not the closed structure. The normality conditions are not satisfied. Well, the right normality condition, yes, because that's internal to the category, so it's lifted automatically. But left normality and associative normality are not satisfied. In particular, there's one map in the codomain of the morphism associated with J, which is not coming from a map in the domain. This can be checked explicitly, so there's no way to make this bijective. Okay, now what can we say about these Gabi algebras? As bialgebras always give a category of modules which is monoidal and for free left and right closed, then Gabi algebras satisfy something similar. So let's take an A module, so a module over a Gabi algebra. Let's consider the A module based on the vector space A tensor M with this bimodule structure here. And one can prove that this always provides a left adjoint to the internal home that we just lifted. These are unit and co-unit, but the point is that if we remember the theorem by Ustalo and Zellman, Beltri and Zellman, we have an adjunction, we have a skew closed structure on the home, then we have a skew monoidal structure on the tensor product. And this is exactly what we get here. The category of modules over a Gabi algebra is always skew monoidal. The tensor product is given by this colorful formula. And these are the left-right unit constraint and associativity constraint. And in particular, the left one is not an isomorphism, for instance, for one-sided Hopf algebras. Now, Since our examples are Hopf algebras and one-sided Hopf algebras, one might wonder how far are we from Hopf algebras then? To answer this question, let's proceed step by step again. So let's first of all consider the counterpart of the Hopf-Galois map, so the canonical morphism that uses A plus A minus B. Let's call antipode the map that we get by plugging the counit on the first leg. This is not an antipode in the classical sense, but just for the sake of being familiar with the notation. Then what we can prove is that if beta is invertible, then we can construct a comultiplication. This is not necessarily left counital, but if it is also left counital, then the Gabi algebra structure comes from a Hopf algebra structure. And this can be used to prove that, for instance, there are no commutative examples of a Gabi algebra. In the commutative setting, any coordinate ring, if it is a Gabi algebra, then it is automatically a Hopf algebra. Other possibility, finite dimensional case, let's try there. If we have a finite dimensional Gabi algebra, it's enough to ask the antipode to be invertible, and then for free this is coming from a Hopf algebra structure. Okay, then let's try a different approach. We lifted the skew-closed structure, but we forgot the normal structure. So what can we say if we also want to lift the normality conditions? So the left normality, and associative normality. Well, it happens that lifting the associative normality corresponds to the bijectivity of beta, the canonical map. If we have associative normality, also lifting the left normality gives us, in fact, a Hopf algebra. So if we would like to call normal Gabi algebra a Gabi algebra for which we lift the whole closed structure, then, as I said at the very beginning, everybody knows what a normal Gabi algebra is, because it's nothing else than a Hopf algebra. In particular, if we are given an algebra, and we ask that the category of modules is closed with a strictly closed forgetful functor to vector spaces, this can happen if and only if A is already a Hopf algebra. So without mentioning the monoidal structure, we lift everything for free. And I think that's all, but don't clap. Wait a second, because there's an advertising moment taking the last moment. We are going to organize a Hopf algebra conference in Brussels next April. We are still considering organizing, gathering funds, so on and so forth. So it's not official, but if you are interested, please express your interest on our webpage so that we can count how many we will be. And thank you very much.
Are there any questions, remarks? Thomas?
Okay, thank you very much, Paolo. Since the main ingredient in the construction of the Gabi algebra, it seems to be a Hom functor. So is it true or not that contramodules would be more natural for the representation theory of Gabi algebras rather than comodules?
Very nice question. We didn't think about it yet. So I hope I will be able in the future, maybe before next conference, to have an answer to this question. But at present, I have no idea.
Thank you.
Can you show maybe the definition again of a Gabi algebra? I was wondering if it is self-dual, or do you have a Gabi coalgebra as a separate notion?
We have a Gabi coalgebra as a separate notion.
Okay.
It would be a coalgebra together with a map that goes from A coop, well, from C coop to C, satisfying duals of these properties.
Okay.
And in that case, you would get for free that a co-commutative Gabi coalgebra is automatically coming from a Hopf algebra.
Okay. And I was wondering then, if you take the dual definition, the Gabi coalgebra, and you read it in the category of sets, or a category with products, what do you get?
For sure, with this definition, you get a group. With the dual definition, I don't remember.
Okay. Because I know some people, Jan Elitze and his son, who's also a category theorist.
Yeah.
At some point years ago, the son, Surab, he was looking at abstracting the axioms that subtraction. So if you have a set, you have say an abelian group, but then you consider subtraction.
Okay.
Right? And you try to write down the axioms that it satisfies. And then there is such a thing. So such a notion exists. I don't remember how they call it, a subtractive something. And then they were considering defining an extension of that to monoidal categories, which perhaps coincides with the Gabi coalgebras. Perhaps, given that your example, if you show the example that you had coming from Hopf, if you dualize that...
this one, you mean?
Right.
Okay.
So if you dualize, you'd be twisting the multiplication by means of the antipode, right? So that's subtraction.
Okay.
In the set theoretic case, it would be subtraction.
Sounds very interesting. Thank you very much. If later you can give me the reference to the paper where it
Yeah, I don't know if there is a reference, but I know they were working on it.
Okay. Well, in the worst case, I will send an email to him directly asking which progresses they have in that direction. Thanks a lot.
Any other?
Can you prove the last results for Hopf monads as well? Or did you work this out explicitly only for Hopf algebras?
You mean the fact that if I lift the whole closed structure, then I have a Hopf monad?
Is there a notion of a normal Gabi monad and it turns out to be a Hopf monad?
Well, if I remember correctly, the paper, we didn't introduce it in the paper, so we have directly the lifting at the monad level. So in a certain sense, you can call it a Gabi bimonad, if you like. And then I don't think we explore the case of Hopf monads. We know that Hopf monads do provide examples of a monad satisfying our conditions. Simply, the map S would be the inverse of the H map for the Hopf monad. Thanks.
Any other question? Okay. And remarks?
Okay. Is on? Okay, so we are discussing about the monad stuff. It's an old paper of Mordich, I think is the pronunciation, from the 80s, if I remember well, published in Journal Pur and Apply. So there is this characterization, and I think it's the first place when the notion of Hopf monad was called, but it's not the Hopf monad that we know now. It's the bimonad, yes. And this is the characterization. When you have a category and a monad, then a category which is monoidal, and we take the representations over the monad, then we have a monoidal structure on the category of representation such that the forgetful functor is monoidal if and only if the monad is a bimonad. So it's close to what you have here. You added the skew stuff, the internal.
Yeah, and you saw from the close stuff.
Because I recognize are 7 or 8 conditions, and part of them I could recognize on your slides.
Okay, any other questions?
Thank you.
Now we send the speaker again and all the speakers.
Thanks to you.
We start, yeah? Okay, so welcome to this session of our conference. I will be a chairman. My name is Sergei Silvestrov, and I'm a chairman. And our first speaker is Andrea Appel from University of Parma. and he will speak about the R matrix of the affine Yangian. Yeah.
Okay. So thank you very much for the introduction. Thanks also to Alessandro and Claudia for the opportunity to be here. It's a pleasure to be in Ferrara. And so today I will talk about the construction of the R matrix for Yangians of finite type and the extension of the construction of the R matrix to the affine type. So it will be on some of algebra which are a little bit more exotic. So just to give a brief review of the history, this is a very old story. So of course everything starts from the Yang-Baxter equation and from the notion of an R matrix, which we have seen already in various flavors. In my case, what I'm interested in is some definition that did not appear yet entirely in this generality. So for me, an R matrix is in fact a function from C, so it will depend on a complex parameter with values in the endomorphism of a tensor product of a vector space. Generally, the vector space would be finite dimensional, but this is not really entirely a restriction. And then, since this function will take values in matrices, we can look at the entries of these matrices, and according to the dependence of the entries by the complex parameter, we would say that our R matrix is indeed constant or rational or meromorphic or in fact formal if indeed I'm not really considering C, but maybe formal series in this parameter. And this function R will be called again an R matrix if it satisfies this cubic relation that again we have seen. So as you see, we have the usual dependence with the indices 1, 2, 1, 3, 2, 3, and this, of course, how do we read this equation? Well, the indices correspond. This R is in fact an operator in two legs. And then I can imagine that these two legs, if I look it on V tensor V, I can think of this leg acting on the first component and the third one, first and second and third, and so on. So this is how you read this identity. And the identity is made more complicated again by considering the dependence on this complex parameter. And now this equation, as has already been said, this appears in physics, in particle physics in particular. This in fact appears when you consider particles moving on a line, and then when you have three particles crossing each other on these lines, then there are some so-called factorizable condition, which is represented by this equation. So this is indeed a very old story. It's before in the 70s, but even before. And why this equation is so special? Well, the first thing to observe is that if you look at this, what do we have? Well, our R, in fact, it depends on n to the fourth variables, right? Where n is the dimension of our vector space. But then, when I look at this equation, I will have n to the sixth condition. So, naively, this equation is incredibly overdetermined. So naively one can think, well, it may be very hard to find solution. Of course, one is a solution, but it may be very hard to find a solution. For this reason, one can think a solution of the Yang-Baxter equation are in a certain sense special. They appear from integrable system, and so in this sense, one can say integrable system, again, are special because they produce this such a solution. So the problem in the 80s was exactly how can I find a sort of systematic way of producing such R matrices. And the observation was that if our vector space is equipped with an extra symmetry, so in particular there is an algebra acting on this vector space, which now is a module, then in fact the existence of this extra symmetry may force you, so may take a lot of space, and so may lead you to actually find this solution. This was systematically solved by Drinfeld, and Youngians were indeed this Hopf algebra that Drinfeld introduced precisely with the aim of solving this problem systematically and, in fact, universally. So let's try to explain this in a little bit more precise way. So what is, first of all, the Youngian? We start with a finite dimensional simple complex Lie algebra. H bar will be a deformation parameter. For the moment, you may think of this deformation parameter as being formal. So in fact, our base ring will be formal series in H bar, or we can think of H bar as being just a complex number. And so we will have an actual algebra. So what is the Youngian of A, of our simple Lie algebra? The Youngian is an infinite dimensional algebra that can be presented in many different ways, explicitly by generators and relations. At some point, I will show you the actual presentation. But in the case of the simple Lie algebra, this Youngian of A has a sort of a more conceptual definition. So it is, in fact, an Hopf deformation of the current algebra U of AZ. So what does it mean? Oops. So what does it mean? We consider A our simple Lie algebra, then we take polynomials valued in A, and then we extend the Lie algebra structure to AZ, and then we consider the enveloping algebra of AZ. So this is already pretty big monster, and then the Youngian deform the standard of algebra structure on the enveloping algebra. So in a certain sense, it has a very similar flavor as usual Drinfeld-Jimbo quantum groups. Now, why the Youngian is, on the other hand, a bit more special? Because AZ comes with a standard grading, and then, in fact, Drinfeld proved that this Hopf algebra, U of AZ, has a unique so-called homogeneous quantization, meaning I can construct only one, up to isomorphism, only one Hopf algebra that deform U of AZ compatibly with the grading. So again, this is another reason why it's not really necessary to say precisely what the Youngian is. The Youngian is characterized by these properties, the unique Hopf algebra deformation, homogeneous Hopf algebra deformation of the current algebra. So it's a very canonical object. As we are working in the current algebra, I can think in AZ to consider classically a shift map, meaning I take my variable z, and then I can shift it in z plus s, where now s is maybe just a complex number, okay? And the Youngian, which again now is this non-commutative, non-co-commutative of algebra, is also equipped with a one-parameter subgroup of algebra automorphism, which I will denote by tau s. Where is it? Here. I will denote by tau s. This tau s, I can think of it again in two ways. One is numerical, one is sort of more formal, according to the quality of this parameter s. And if s is just a number, then again I will have an automorphism of the Youngian. But if I can think of s as just a variable, then this shift automorphism may be just a map from the Youngian to polynomials in the Youngian. Okay? Now, when I have this shift automorphism, how do we use it? Well, just for the moment, just for the notation, what do? We take the coproduct that we know comes with the Youngian, and we can shift it in one leg. So only in one leg, we apply tau s, for example, on the left leg. And now this gives me a coproduct that now also depends on a parameter. So as an operation, is slightly different from just saying this is just an Hopf algebra. This comes with a family of coproduct, and so I can consider this delta S. Okay, so Drinfeld theorem, proved in 1985. In fact, this is a theorem that never really appeared. This is something Drinfeld wrote in his ICM paper, but the proof of this theorem never appeared for a long time, and only recently Pavel Edingov sort of translated the notes of Drinfeld from Russian, and then a PhD student of Alberto De Sole sort of included this translation in his PhD thesis, and so finally we can read the proof. So what is the statement of this theorem is the Youngian as an R matrix, in fact as a universal R matrix. So what does it mean? It means that in fact there exists a unique formal series which I denote RD, D stand obviously just for Drinfeld, which is a formal series in S inverse with values in the tensor product of the Youngian. And this operator satisfies this long list of identities. And of course, if now you sort of cover your eyes and forget about the S, you will immediately see all the usual axiom of a quasi-triangular Hopf algebra that everyone has seen many, many times. So we have the intertwining equation of R. So this operator is twisting the coproduct to the opposite coproduct. And then I have some cabling identities or some coproduct identities whenever I apply the coproduct to the left leg or the right leg. And now the usual one-line proof shows that, for example, if I have the intertwining condition and the coproduct identities, I know that R satisfies the Yang-Baxter equation, as I wrote in my previous slide. So in fact, this operator that Drinfeld constructs satisfies 3 more compatibilities, which indeed are less common. The first one is the unitarity condition, meaning if I compute the inverse of this R matrix, which is still going to be a series in S inverse, this corresponds to the opposite R matrix. So I just flip the two components, but now will be in the parameter minus S. And then also the R matrix is invariant under translation. So I can now shift both legs of the R matrix by A and B, and these affect only the value of the parameter. So this corresponds to just the original R matrix, now evaluated in S plus A minus B. Just to convince you that this S to the minus 1 is actually important, well, you see it immediately here. If I want to give a meaning to this translation invariance, I really need to expand in S inverse. I cannot expand in S. That will not give me a formal series. And then finally, there is one last condition, the linearization condition, that is telling us that if I expand in S inverse, the linear term, the coefficient of S inverse, is actually given by the Casimir tensor of my simple Lie algebra. This is what omega A is. It's just the tensor product of the basis and dual basis. Okay. So this, of course, gives what? Well, this is in fact something that I can think as an operator valued in algebra. So if I have a module over the Youngian, or a tensor product of modules over the Youngian, I can evaluate this operator on this tensor product, and I get, on any module, I get a solution of the Yang-Baxter equation. Now, at this point, the solution that I get, it's only formal, because I start, indeed, from a formal series in S inverse. So when I evaluate, it's only a formal R matrix. One comment about this proof, indeed, the proof of Drinfeld is entirely cohomological and relies on the fact that A is indeed a simple Lie algebra. Simple Lie algebra are rigid, and this notion of rigidity can be extended to the Youngian, and Drinfeld prove that indeed you can construct a unique element that satisfies these properties. And to this end, really, this linearization condition is crucial. So this is formal, so it's not really entirely satisfying for our purpose. So what happens? Well, it happened that then Drinfeld proved that if I give you now an irreducible finite dimensional module over the Youngian, which there are a lot, in fact, there are continuous families of irreducibles. So irreducible, the finite dimensional representation theory of the Youngian is incredibly rich. If I give you an irreducible finite dimensional module, then this formal R matrix that Drinfeld introduced, in fact, can be factorized in this product, D and R. And what happened? That R, the straight R, is in fact a rational R matrix. So it's really an expansion of a rational function. So remember that all the entries will be rational function in S, and then you can expand all the entries as a formal series in S inverse, and you will get the action of R. And then this D, instead, this is quite interesting, this is just a scalar correction. On the other end, this is going to be a divergent series. So this is really something that if we want to give some meaning to this operator numerically, we need to kill it. So we can normalize it, remove this scalar factor, and indeed we find a rational R matrix. So it was possible to find a solution of the Yang-Baxter equation with rational R matrix on any tensor product of irreducible modules over the Yangian. This was in fact the main result of Drinfeld. And here you have the simplest case for SL2 and its two-dimensional representation. I can extend it to an action of the Yangian on C2, this two-dimensional representation of the Yangian, and then you can compute this R matrix essentially by uniqueness of this operator. This is what Koroshkin and Tolstoy did in '96. And you can see that this is the explicit expression of the divergent series. It's a product of gamma functions. And then the rational R matrix that we find here is in fact what is called Yang R matrix. So this was the simplest solution, something like the simplest solution of the Yang-Baxter equation. And this was in fact the motivation of the name of this algebra. This is why Drinfeld decided to name this algebra Yangian in honor indeed of Yang R matrix. Okay, so our problem is indeed try to, well, first we would like a better expression of this R matrix, meaning, okay, Drinfeld theorem is fantastic, but in a certain sense, again, the origin is cohomological. We would like a more explicit expression of this operator, which at the moment is kind of a mystery. We can focus on a single representation, and maybe with some lot of work we can produce, we can actually compute it. Again, something like a posteriori computation. We deduce this identity by uniqueness, but we would like a more explicit expression. And then the second problem is, are we really bound to the word of simple finite-dimensional algebra, or can we extend it to Kac-Moody algebra? This would be the other big question. And so, as I promised you at the beginning, this is the actual presentation of the Yangian associated now to a general symmetrizable Kac-Moody algebra. So here, this Aij correspond to a generalized Cartan matrix. GKM is the associated Kac-Moody algebra. And well, the Yangian is just this algebra, which is associative algebra, which is presented by this Cartan subalgebra. So I have all the elements in H, and then I have these operators, this generator, infinitely many generators, XIR plus minus and XIIR. And the presentation of the algebra can be done more efficiently by pack all these infinitely many generators into generating series and write down all the relation into relation between this generating series. This is how you read this slide. If you look at this slide for sufficient amount of time, you start to recognize the usual pattern of relation that you find in simple Lie algebra. So you will have a commutative part, which is given by the xi's and then by the h of my usual Cartan subalgebra. So all this is commutative. The h keep acting diagonally. The xi, not really, not entirely diagonally, okay? But they keep commuting with the h, and so I have this very big commutative subalgebra inside the Yangian. And then, of course, since there are all these plus minuses, I also can recognize a sort of a positive part of the Yangian and a negative part of the Yangian and an abelian part. So there is a triangular decomposition. Now, when G is in fact simple finite dimensional, we know, using another presentation, not this one, we know that the Yangian is an Hopf algebra. We have an expression for the coproduct. When we decide to take this presentation of the Youngian that Drinfeld produced and just brutally, naively extend it to any cat smoothie, we have no idea if this coproduct still exists, because in fact the coproduct, even for the Youngian of a simple Lie algebra, does not have an explicit expression in terms of this generator X. So a closed formula for this generator is not known. So one problem was indeed to say, okay, is it true that this object, this associative algebra, is indeed an Hopf algebra? And so this was partially solved by Nicholas Guy, Nakajima, and Ventland in 2018, in which they proved that not really for all cat smoothie, but for a good class of cat smoothies that include a finite type and, of course, a affine type, indeed, you can construct a coproduct, which I call the cat smoothie coproduct, which is defined by this formula that you see here. Now, of course, the formula, just for record, just to say this is defined in this way, but it's pretty hard to digest it in 1 or 2 minutes. We can recognize, of course, that there is a good expression, so the Cartan clearly is primitive. These elements are primitive only when r is equal to 0, and so it corresponds more or less. There is a z here, as you see. And then this Ti, which is another class of generator, in fact, they correspond to the logarithm of the abelian part, is given by this formula. They have something which is barely manageable as an expression. It's relatively simple. Now, you see that here, in fact, I don't have an actual coproduct. I have something which is also a topological coproduct, because there is now this other parameter z. And this operation now is valued in Laurent series in Z, valued in the tensor product of the Youngian. Now, this is needed by this expression that you see here. You see that here there is a sum over beta, which are positive roots of my cat smoothie. So clearly, if my cat smoothie is finite type, this is a finite sum, and there is no problem. There is no topological coproduct. There is an actual coproduct. You can set Z to 1 and remove it. But otherwise, if G is not finite, then this is an infinite sum. And so I need to introduce this parameter Z to make sense of this infinite sum. But I can do it. I get a topological coproduct. I say, OK, so can we still do tensor product of representation now with this guy? And the answer is yes, almost. So assume now that G is our affine, it's of affine type, just to simplify our life a little bit. And we want to consider some representations of the Youngian, which are not now finite dimensional representation, maybe are not really there. So what we consider are so-called category O representation. So the Youngian contains a copy of the original Lie algebra. And so I will say that the representation over the Youngian is category O if the restriction to the Lie algebra is in category O. So it's a weight module with a usually con condition. No? It's basically the category, let's say, generated by the Verma, just to make it naively. So if I have this con condition, then at this point, the topological coproduct that I told you in the previous slide truncates, because, of course, what you see is that my Casimir here is also polarized. This is, in fact, when I wrote omega beta, this means that I have the left leg is as weight beta, and the right leg is weight minus beta. So if I have the con condition, this infinite sum is going to truncate, and so I have an actual coproduct. So in fact, using this topological coproduct, I can construct a good tensor structure, monoidal structure, on the category representation of this beast. And this will be the first structure that we consider on representations. So in fact, here what we have is that there is something which is a little bit more poetic. So this is not really strict, it's just poetry. I would say that the category O of the Youngian is a polynomial tensor category using this action, which what does it mean is that I can take the tensor product of two representations. I will write V tensor S W, and by this I mean take V, shift it, so I can do the pullback with respect to the shift operator. I can do the pullback with respect to the shift operator, this is what Vs is, and then take this tensor product. What does it mean, polynomial? Well, polynomial means that you can try to write the usual axiom of a monoidal category with this new structure, and this is what the identities that you get. You get some sort of mildly different set of axioms that in a certain sense you can understand. Now notice that the core of the problem is that here, whenever I say I have this polynomial structure, what does it mean? That I have an object, which is the vector space V tensor W, and this tensor product is endowed with a family of action that depends on S. And therefore, again, I can ask, okay, if all the entries of this action are going to depend on S, and again, I can say the action is polynomial if the entries are polynomial in S. And this is what you get in this setting. So the question of Drinfeld, find an R matrix for the Youngian, becomes, is it true that, in fact, this category is a braided tensor category? Now, on the other hand, there is this parameter. So braided, again, does not really mean anything, and so we will put another adjective here. We would like to put polynomial, but polynomial does not work. We would like to put rational, but rational does not work. We need to put meromorphic, in fact, to prove it. So the R matrix will be, in fact, a meromorphic function. So how do we construct the R matrix? The R matrix is constructed in this new approach, is constructed by relying on another fake tensor structure on this category, which is given by a different topological coproduct, which is known as Drinfeld coproduct. This Drinfeld coproduct is similarly defined by some expression, but what happens and what is different is that when now I go to evaluate on a tensor product of representation in category O, the entries are no more polynomials in S, but in fact they will be rational function in S. So this Drinfeld coproduct is defining some rational tensor structure.
The fact that you have the square bracket open there and two square brackets on the left means that it...
Meaning this is formal in S inverse and polynomial in S.
Yeah, that's what it
Yes.
means.
And so the trick is the following. We are interested in the magenta arrow. We are interested in constructing an R matrix for the Kac-Moody coproduct. But we don't know really how to do it, if not in the finite type following Drinfeld result. So what we do is that we now throw into the game even Drinfeld coproduct, and now you split your problem into two subproblems. First, we would like to find an R matrix for Drinfeld coproduct, R0, and then you want to construct a twist that relates one coproduct to the other. So now you have split everything into two subproblems, which are in fact simpler to solve. And this eventually is and then your R matrix, you will get it by composing these arrows. So automatically your R matrix come with this sort of Gaussian decomposition, this triple tensor product, this triple product. And so this eventually is the final, fantastic. Okay. This is the last slide. So eventually this is indeed the problem. As I said, we split everything into these two subproblems, which are basically construct R0, the R matrix for the Drinfeld coproduct, and then construct a twist that relates the two fake Hopf structure that you found. And so this is indeed the result. So we are able to produce for any V and W in category O, there is a meromorphic function curly R, which is given by this triple product, where in fact all the factors, this is not written, are natural in V and W, but it's really a construction in representation. And what are all these things? Well, R0 is indeed an R matrix for the Drinfeld coproduct, which on the other hand, when you evaluate on representation, the entries of these operators are meromorphic function. And this first piece of information, we construct it, in fact, using complex analysis. We look at some special difference equations that appear in the theory, and then we're going to use complex analysis to consider some fundamental solution, and this gives us R0. Now, two observations on R0. The first thing is that our construction over 0 works whenever my Lie algebra, my Kac-Moody algebra is a simple Lie algebra, so again I get Drinfeld result, or it's a Lie algebra of affine type, except SL2 affine, so except the simplest case. We get everything, but not the simplest case. This is due to the fact that our difference equation, the coefficient of our difference equation, are determined by the determinant of the so-called Q-Cartan matrix, at the formation of the Cartan matrix. For SL2 affine, the Cartan matrix, of course, at determinant 0, is Q-Cartan matrix still at determinant 0, and so this difference equation gives absolutely no information. But in all other affine type, these actually give a regular difference equation that you can solve. Other interesting thing, this fundamental solution, they give you meromorphic solution, but if you now consider a tensor product of highest weight module, as in Drinfeld case, you can normalize this meromorphic function and reduce it to a rational R matrix. The second and last piece is in fact what R minus is, and then R plus, of course, is basically J2 inverse. And R minus is a rational twist that relates the Kac-Moody coproduct with the Drinfeld coproduct. And this also is very explicitly determined by a recurrence relation that, again, you cook up from this intertwining relation that you want to solve. Again, two considerations of R minus. The first one is that this construction of R minus is specific to finite and affine type. So I'm done. To finite and affine type. So in particular, we don't know how to extend it beyond this to indefinite type. And then the last, very interesting aspect that we have no idea how to explain is that this rational twist has no expansion in h bar. You cannot set h bar to 0. This expression will involve 1 over h bar, so we need to consider it a numerical parameter. However, miracle happens. And so if you evaluate this twist on a tensor product of highest weight module, these components with 1 over h bar disappear. They go to 0. And so, in fact, your R matrix is, in fact, still you can expand it in h bar, and their limit, of course, at h equal to 0 is still 1, as you expect it to be. OK, and then I stop here. Thank you.
Questions, comments, remarks, solutions?
It's more the clarification. If you could go back to the slide where you showed the presentation of the Youngian for the Kac-Moody. Yeah. So the relations for psi I, psi j, do they depend on the same?
Oh, no, no, no. This is psi iu and psi jv. Thank you.
Okay. Thank you.
So your solution is completely constructed. Do you understand it? I mean, the last result.
Let's say
so if you put inside an affine, you get automatically, explicitly a solution, or there is still some?
Well, of course, what happens, as I said, R minus, as I said, this is a recurrence relation that you can evaluate on representation. It becomes simpler, and you can solve it there, and you know the solution is unique, so you're OK. So this, I would say, is rather explicit. And this one, on the other hand, it depends how much you like, again, fundamental solution constructed in complex analysis, and you can decide if this is enough explicit for you. But I would say, with respect to the Drinfeld result, this is very explicit. And in fact, the operation that we get here is, again, is meromorphic as an operator. If you expand in S inverse, then you can, in finite type, you can compare it with Drinfeld solution, and you will find that this expansion in S, they actually coincide in finite type with Drinfeld solution by uniqueness. So this is indeed sort of improving and generalizing Drinfeld result in this sense, yes. As for computing it, for example, for a fine Youngian, having representation where to actually compute this solution is not so easy to deal with. All representations are going to be infinite dimensional and not very easy to manage, so producing solution is kind of hard except for some case.
Can you apply your approach also for the affine GL1 case?
No.
Why not?
Same reason with the difference equation in a certain sense. This difference equation depends again on your Cartan matrix, because you need, I mean, we have this difference equation to look at. We do not have an analog for GL1. So at this moment, that one we cannot do it as well.
It's just a basic question about something you had at the beginning. You mentioned that the uniqueness of the solution is due to the fact rigidity, so cohomological reasons. But what cohomology is involved? Of what?
It actually relies on the fact that here you're looking at AZ as a bialgebra, as a Lie bialgebra. You consider this, I didn't comment on this. This is the expression of the LICO bracket for the current algebra. And Drinfeld developed an ad hoc cohomology for AZ that actually uses in his construction. I should confess that I tried to read Matteo Gardini's thesis, where Drinfeld proof is allegedly reported. I didn't really verify, but it's not entirely clear how to prove it precisely. But the idea is there, the cohomology is described there, and this is what is behind.
Okay, thanks.
No more questions, and let's thank. So our next speaker is Walter Ferrer Santos from Uruguay, and he will talk about the representations of not affine schemes, Hopf sheaves. Okay. Oh, it was not on. It's completely switched off. Yeah. Okay, so I will announce. You tell me when I should do it again. Okay, so our next speaker is Walter Ferrer Santos from Uruguay, and he will speak about representations of not affine schemes, Hopf sheaves. Okay.
Well, thank you very much. I'm very glad to be here with so many friends and well-known mathematicians. So I will speak about representation theory, basically. As the title says, representation of not affine schemes. And this is joint work with some colleagues from Uruguay and Mexico. Well, I put lots of information in the slides, but you don't have to read it. I will summarize it, basically, if I can. So this is joint work with Pedro Luis del Ángel and Álvaro Ritatore from Mexico and Uruguay, respectively. And we want to study the representation theory of non-affine group schemes. So the representation theory of group schemes, affine, is completely developed due to the work of many well-known mathematicians in last century. And but when one wants to step ahead of the affine schemes and do some representation of non-affine schemes, one finds immediately some strong difficulties that are not easy to solve. The main reason is, I say there, that the affine schemes have many polynomial maps, and the non-affine schemes lack enough maps, polynomial maps, to separate the representations, to work with them, etc., etc. This is informal, what I'm saying, but basically that's the main difficulty. So the point is, well, what type of non-affine schemes we want to represent? What are the objects to be represented if we don't deal with non-affine scheme? If we deal with non-affine schemes? Basically, we look at the theorem, a theorem called Chevalier theorem, but in fact is due to many people, Barsotti, Rosenlich, and others, was stated by Chevalier early, and then many proofs appeared before he wrote his own proof. So this theorem somehow shows that any non-affine scheme can be split in two parts, an abelian variety A, and something that can be called maybe the, how do I call it here, the affine radical. So the basic property is that A is an abelian variety and GF is an affine group that is normal in G. An affine group scheme, whatever. The theorem of Chevalier was initially proved for group schemes of finite type. More recently, it has been generalized. And basically, one can say that a version of Chevalier theorem can be obtained for any quasi-compact group scheme. So our platform, a priori, will be the platform G will belong, digamos, let's say, to the set of quasi-compact group schemes. And it can be proved by basically all of them. There are some exceptions. One has to take certain care. But the main thing is, for any quasi-compact group scheme, there is an associated affine variety and a faithfully flat map from Q from G to A. That is a morphism of groups. And so it seems clear that the object to be represented is the map Q. So the representation theory of non-affine scheme will be the representation theory of Q, where Q is a map from a quasi-compact group scheme to an abelian variety. So, if one wants to do some representation theory, one has to set up a platform of monoidal categories. The theory of, we will define, the category we want to consider is the category, as I said, of Qs, morphisms of group schemes where X is compact, A is an abelian variety, and that's it. We can ask or not the map to be faithfully flat, but it's not strictly necessary to have this hypothesis. So we will produce in the schemes over A, the family of these arrows Q, we call it the schemes over A. And we want to produce in the category of schemes over A with a natural morphism a monoidal structure that is very easy to define. Simply one, all the schemes are over K, a base field. Then what we have to do to produce the monoidal structure is the operation will be called X twiddle, and is simply the Cartesian product of the morphisms over the basic field composed with the multiplication or the addition of the abelian variety. So the product of the objects XA and YA is this arrow F twiddle G. And this is the monoidal structure. The unit is the zero object that as is written down there. So we want to produce monoids in this category, and it's very easy. One just writes down the definition and ends up with the assertion that the monoids are what is written in the last two diagrams. A monoid with respect to that product is, with respect to that monoidal structure, better said, is a morphism M of the varieties over Q, over K, the basic field, and that certifies a commutative diagram like that, a compatibility condition that basically is saying that M is a morphism and S is a morphism. We know that S is a morphism of group of monoidal objects, and this compatibility with the maps Q, and the unit object is the one defined in the other triangle for the monoidal. Now, MA is a monoidal with respect to the monoidal structure of the category. There is another product in here that we need to introduce in the same category of schemes over A. That is the product in the category, the fiber product over A. The structure of schemes over A has a product, a Cartesian structure, and this is the product, the fiber product over A. So we are dealing, in fact, with two monoidal structures that we need for our definitions, and these two monoidal structures are can be considered a duoidal structure. Every time we have a monoidal structure in a Cartesian category, if we consider the monoidal structure given and the new one given by the Cartesian structure, we have a duoidal category. This is something that appears in the literature. So in that sense, when we passed from, in the case that A is a base field, K, what we have is just the two structures coincide. If you look at the definition I just wrote, in there, and this new one, both definitions coincide. The two products coincide. So in other words, the cost of going from affine situation to non-affine situation is to do the representation theory not in monoidal categories but in duoidal categories. So in that sense, this is another example of what Marcelo mentioned during his talk, applied to representation theory of schemes. The use of duoidal categories for the representation theory of scheme. Well, any representation theory has a, well, almost any representation theory searches for have a sort of duality, and we will, between the geometric objects and the algebraic objects, like groups and Hopf algebras, algebraic groups and Hopf algebras, schemes and some algebraic category that I will characterize. And this has to do with Zariski-Grothendieck duality. It is well known that the category of affine algebraic groups and the category of the opposite category of Hopf algebras, to all Hopf algebras. My assertions are being restricted to the groups, to the monoidal objects. So there is a duality between these two categories. That is the duality, classical duality by Zariski originally, and then generalized by Grothendieck. And Grothendieck defined all this situation, the global spec, and that is in the lower here, the global spec and the global polynomials over a scheme, or that is a sheaf, in fact, between two categories, the category of schemes over A that we were considering, and also the category of QA mod op. These functors form an adjunction that if we restrict further, instead of working with quasi-compact schemes over A, we work with affine schemes over A. I didn't say what is an affine scheme over A. It's not an affine scheme. It's a affine scheme over A. Means that the map Q, the morphisms Q from X to A is a affine map. An affine map. That means that basically that the inverse image of an affine object in the codomain in A is pulled back to an affine object in the scheme, original scheme X. So this is, if we restrict, that's all work of Grothendieck. If one restricts the morphisms to affine morphisms, we get an adjoint equivalence between both categories. So this is the generalization. Of course, Grothendieck established his theory for any scheme S. The particular case to consider this duality, given in the form of this adjoint equivalence between these two, the geometric and the algebraic part, the role of A here is the possibility of giving another monoidal structure to do the representations. A is what provides the new monoidal structure. See. Oh, the right-hand side, sorry, is the quasi-coherent shifts of OA modules. This sounds like rather a strange name, but basically means the shifts that when we look at them locally in the affine pieces of the scheme are just the modules, the shifts associated to a module over A. If we are dealing with the spect of A, a quasi-coherent shift over A is in the local case is associated to a module. This characterizes the quasi-coherent shifts. Okay? When A is trivial, so you don't have you have only one point, the variety reduces to 1 point, and so you have only one fiber, and this fiber corresponds to the right side in here. In the other side, you get simply, if A is a point, you get simply an affine scheme. This fiber, here or up there? By definition. By definition. Well, maybe I should have put algebra here, not model. See, by definition, it's an algebra. Sorry. How I am doing time? Okay, so what we want to do is to see the duoidal structure that we had in the left-hand side. We want to see it in the left-hand side. What corresponds? And so there is a theorem that says exactly in this context, in which we are dealing with an adjoint equivalence between the geometric part and the algebraic part, we can transpose, let's say, the operations from the schemes that geometrically are very easily defined to the other side, and by this translation from the left to the right, we get what we call the Hopf shifts that I want to define. I'm defining the objects that we are going to represent. So I'll go up to here. So what are the ingredients of the, when we do these translations, we pull to the other side the structure, the two products we have defined for schemes of A, we'll get the sheaves and the structures at the level of the sheaves. So the structure at the level of a sheaf consists in this data here, that is a sheaf of QA algebras, now I wrote it correctly, a comultiplication that will be a map from H to S star of H cross product H, a multiplication that is a usual multiplication in the usual sense. Then we have a couple of units that we need for both monoidal structures. One for the canonical product, that is UH, and the other for the new product, the one that is square tilde, that is the skyscraper sheaf. And then we have the antipode. As you know, and that was mentioned during Marcelo's talk, to define the antipodes in a B-monoid in general is hard. In this case, it's not that hard because we are guided by the geometric case in which the inverse has to be the inverse at the level of the object, so of the basic object. So one can define more or less easily the antipode. I won't enter into details about that. Basically, the antipode will be a map from H to op H. What is op H? Op H, we have the map at the basis, is the last here. Is the opposite map at the level of the basis, that is the projective, the abelian variety A, the opposite, and then we push, given any QA module, we have this pull back and push forward functors, and that coincide because op is invertible. So we push from the original H from QA to QA via op star, and then we get the antipoda will have to be a map H from sigma H from H to H op star. I should say some words about the definition of this twiddle square product. There is a construction due to Grothendieck also. I think I explained it somewhere. Yeah, here, at the end. So if we have two sheaves of QA modules, or modular algebras, F and G, we can produce what is called the external tensor product, that is a sheaf on QA times A, that is defined simply by taking F in the first component, A, pulling back by P1, by the projection, and here we produce a sheaf on A times A. The same thing here, then we perform the product of these two, and this is what is called the external product. It's an operation that a sheaf on X and another sheaf on Y induces a sheaf on X cross Y. This is similar to a construction with modules and rings. So, what are the axioms? The axiom so this is the definition of Hopf sheaves. The ingredients is the ones I mentioned before. The ones that are in the first square. And of course, we need the condition of compatibility. That is the one written there. The multiplication followed by the co-multiplication. The pentagonal diagram that we need to define the map here. We have to use the the exchange map that mentioned that Marcelo mentioned that interchanges two things: the middle terms that here are the same, so you don't know you don't see the exchange of 2H here, but the products, the two monoidal structures interchange the roles also. So this is the definition of a Hopf sheaf. And now what one has to do to continue with this idea of using this as a platform for the representation theory of non-affine schemes is to consider, well, what are the modules or the comodules? Well, the definition of comodules is natural, is this one that is written here. We need a morphism of sheaves of this type, a commutative diagram like that. And so this is the definition of a sheaf of H comodules. And this will be the setup, basic setup for the representations. I won't speak, I don't have time to talk about the representations. The representations, the work one has to do to define the representation is to define the representation at the geometric level and then transpose them to the algebraic level, and then we have the two representation theories, one for the geometric part and the other for the Hopf algebra part. For the geometric part, the representation are called the fiber bundles, but with certain consistency restrictions that have to do with the maps on the fibers. And this translated to the Hopf sheaves will give a certain family of comodules that will be the natural representation for H. And then this is the platform. All this is just to set up a platform that is, I didn't explain many details, but this explains the platform where we have to start doing representation theory. We have advanced a little in the definition of the representations. The basic thing that we have proved to guarantee that this is okay is to produce a Tanaka reconstruction theorem. We proved at the geometric level, not at this level, at the geometric level, with the groups and the maps Q. We proved a Tanaka reconstruction theorem that allows us to reconstruct the map Q, that is the object we are representing in terms of the family, the category of representations. I think that's all.
Instead? Yeah. Okay, so welcome back from the coffee break. So now we start our last part of the session. Our speaker is Matthias Troinski from Uppsala University, another participant from Sweden, and he will talk about Lux model profunctors, reconstruction, and tensor categories. Okay. Yes.
Okay, so first I'd like to thank the organizers for giving me the opportunity to speak here. It's a great pleasure. And it's also great to visit Italy for the first time in my life. So The title of my talk is Lax Module Profunctors, Reconstruction and Tensor Categories. And I should remember to say that this talk is based on this paper, this preprint, which appeared on arXiv today, in fact, so still warm, and joint work in progress with Tony Thoman, who is sitting there with a dark blue T-shirt and a depressing phrase about grad school. Okay, so let me start with some basic setup. So C is a monoidal category, and M is a C-module category, in some communities better known as a C-actegory. I will denote its action functor by this little triangle here. And for me, the domain of this functor is the tensor product of C and M over K, meaning the objects are pairs of objects, one in C, one in M, and the home spaces are tensor products of the respective home spaces, so that functors from this are automatically K bilinear. And in particular, for every object X in M, we get a functor of acting on X, which goes from C to M. So reconstruction from module categories is the process of determining an algebra object A so that the given module category M is equivalent to the category of module objects over A. The slogan is, module categories are categories of modules. And an early prototypical result of this kind is the theorem of Ostrich, which tells us that if C is a fusion category and M is a semi-simple indecomposable C module category, then there is indeed an algebra object A, so that M is the category, or is equivalent as a C module category to the category of module objects over A. Here, the notions I have used so far, I think were introduced in previous talks, in particular many of them in the talk of Professor Shimizu yesterday. So since Ostrich's theorem, many variants and generalizations of this result have appeared in the literature. So here I list some of those which either I find important or I have learned a lot from, or the bottom item is just shameless self-advertising. So first, there was the paper of Etzinghoff and Ostrich, which generalized this to the non-semi-simple setting of finite tensor categories and finite module categories over them. And there is also a paper of Andruskiewicz and Mombelli, which solves a similar problem, but more explicitly in the case that C is modules over a finite dimensional Hopf algebra. Then there is a paper of Ben-Zvi, Brashear, and Jordan, which tells us how to use Beck's monadicity in reconstruction. A paper of Mackay, Mazurchuk, Mimitz, and Tubenhauer, which uses reconstruction in a completely different setting of so-called two representations, which uses some kind of semi-strange techniques that I learned a lot from. The paper of Douglas, Chomepri, and Snyder was mentioned yesterday by Professor Shimizu, and it contains some very nice partial results for C non-rigid, and this is the setup in which also Fuchs, Schaumann, Schweigert, and Wood work, where they replace rigidity with a weaker duality assumption known as the setting of Grothendieck-Verdier, monoidal and module categories, and the aforementioned preprint of mine and Tony Thoman's also is in the non-rigid setup of modules over bialgebras.
Could you move a little bit to the right, because you are hiding?
Yes, I am. Okay. So let me give a sketch of proof, which kind of illustrates the common techniques for all these results. So first, we want to assume that there is some object X in M, so that the functor of taking the internal home from X is defined. So this is a functor from M to C. And then we assume further that there is a particularly nice object X, so that this functor is exact and faithful. So in other words, that X is C projective and a C generator. This terminology mirroring the properties of home functors or projective objects and generators. And in fact, then we are ready to just invoke Beck's monadicity, which automatically gives us an equivalence from M to the Eilenberg-Moore category of this monad, which I obtained by first acting on X and then internal homing from X. And then rigidity, or the Grothendieck-Verdier structure, gives me an equivalence of, an isomorphism of monads between this strange monad and just tensoring with the algebra object of internal endomorphisms of X. And furthermore, it gives us an identification between the Eilenberg-Moore category and the category of module objects in a compatible way so that we get an equivalence of module categories. So, in particular, the many different various sets of assumptions regarding finiteness on C and M or exactness on the tensor product in C or the action on M are made in order to ensure that parts 1 and 2 work. And then the assumption of rigidity, which I should now mention what that means, meaning the existence of left and right dual objects via unit and co-unit morphisms, aka co-evaluation and evaluation morphisms. This assumption gives us 0.4. So ensures that some strange monad is realized by an algebra object. And now I want to get into technical detail on what this internal home means, because in the literature, two definitions appear. So the first one, notably used in the tensor categories book of Etzinghoff, Geleaki, Nikšić, and Ostrik, is an object which represents the co-presheaf given here. And then we conclude that this is an algebra. If I take internal endomorphisms, this becomes an algebra object because this co-presheaf is lax monoidal. So if you know about algebra objects in day convolution, this will follow through by general nonsense. And the other approach is to assume that this functor of acting on X has a right adjoint, which is then the functor of internal homing from X. And the internal home from X to Y is just the value of that functor at Y. And then this becomes, this monad, which I obtain by first acting on X and then homing from X, is a monad because if I first take the left adjoint and then take a right adjoint, I get a monad. And one can show that this is always a lax module monad, meaning that there are coherence morphisms which are not necessarily invertible. And if C is rigid, I can drop the lax, and that's how I get an algebra object, because module monads are given by algebra objects. Okay, but I want to look a bit closer on the non-rigid side of things. So let's consider a non-rigid example. So let S be the two-element monoid generated by an idempotent element S. And let's consider rep S, so the category of finite dimensional modules over S. This is a semi-simple category. There are two simples, both of them one-dimensional. One of them is the trivial module, and the other is the one-dimensional module where the idempotent element S acts by 0. Then the monoidal structure on rep S is in fact completely specified by the presentation of Grothendieck ring, which is given by observing that the trivial module is of course the monoidal unit, and this other module, which I denote by K group, is idempotent. In particular, in any module category over rep S, K group must act by an idempotent functor in some sense, but of course 0 is an idempotent functor, so it can act on finite dimensional vector spaces by letting K group act by 0. And then, if we consider the former definition of internal home from the previous slide, which is given by representing some co-presheafs, in fact, we can find a representing object. So so K is definitely a generator in any set of assumptions. K should work as X for our previous slide, and we should get an algebra object which should reconstruct our module category. So we try to do that. We find a co-representing object, is the trivial module, and the trivial module is an algebra object in a canonical unique way. We consider module objects over the trivial module, and we get back rep S, which most definitely is not M, which here is apparently shorthand notation for this action on vector spaces. Right, in rep S we have two simples, in vector space we have one simple. Certainly something went very wrong. On the other hand, if we consider the other definition of internal home via the right adjoint, one can convince oneself that the right adjoint exists, and if we compose first acting on K and then internal homing from K, this monad is not isomorphic to tensoring with K-triv. So again, something went wrong. In the rigid setting, we would now just identify this monad with this algebra object and identify the Eilenberg-Moore category with module objects, and here seemingly nothing works. So the problem, this is a bit of a meta comment, is that if C is not rigid, then knowing homes from K to something acts on K is not enough to know homes from something acts on K to something acts on K. If C is rigid, then I can use duals in a nice way to kind of get enough information. However, if we consider this monad, it is in fact isomorphic to cotensoring with K-triv, where K-triv I now view as a bicomodule. Okay, so bicomodules over rep S with the usual coalgebra or bialgebra structure are S bigraded vector spaces. So I can view K-triv as S bigraded by making it concentrated in degree E, so at the unit. And then cotensoring with this bicomodule is the same functor as this monad, which should work for reconstruction. And moreover, this bicomodule structure is compatible with the left module structure in that we get a Hopf module in both ways. So both comparing the left action and the left coaction and the left action and the right coaction. And K-triv is an algebra object in the monoidal category of these gadgets, which I call Hopf trimodules, which are monoidal when endowed with the cotensor products. And this, in fact, will be a general pattern. So given a Hopf trimodule algebra, this is just the kind of natural name for an algebra object in this category of Hopf trimodules. And a module is then a left B comodule, so not a trimodule, just a left B comodule, with an action map from the cotensor product to itself, satisfying the kind of usual natural axioms. Similarly, if A is quasi-finite on the right, we can define the cohom, so the left adjoint to the cotensor, and we can define a contramodule as, again, left B comodule with a map from N to the cohom from A to N. And in fact, the example from last slide generalizes to a nice theorem. So this is from that preprint where our set of assumptions is now quite general because we can handle nice module categories over categories of comodules over bialgebras. So including infinite dimensional bialgebras. So if we have a locally finite module category over finite dimensional comodules and we have an injective generator, a suitably defined injective generator, and this functor of acting on X is exact, then in fact there is a Hopf trimodule algebra so that this module category is equivalent to the category of finite dimensional A contramodules. And I should perhaps, okay, yes, I should mention that this Hopf trimodule algebra then is quasi-finite. Okay. So this leads us to a philosophical observation that sometimes there is an algebra object A for M, but not in C. For instance, infinite dimensional comodule algebras are more generally algebra objects in int-completion or other completions, co-completions of C. Give an example of this, but also if C is not rigid, then we have just seen that we should really look at algebra objects in the category of lax module endofunctors of C, i.e. lax module monads. And so the general philosophy is that we should find a new monoidal category D of C so that nice C module categories up to equivalence should correspond to algebra objects in D of C up to Morita equivalence, where D of C, the notation is suggestive of connection with the Dirichlet double. So since I don't like cliffhangers, this is a result of that kind. So without any assumptions on the monoidal category C, there is another monoidal category T of C, so that C module categories with an internal additive generator identify with algebra objects up to Morita equivalence in T of C, but moreover, we can interpret bimodule objects as some kind of module, actually as lax module profunctors that I will speak of in the next slide. And so we can also interpret C module functors in terms of bimodules and C module transformations. It's a full-blown bicategorical equivalence. So this is also quite important that we get all the functoriality properties where the composition of bimodule objects is the balanced tensor product. So what is this category T of C? It's the category of Tambara modules on C, also known as lax C module endoprofunctors of C. This result I should briefly remark if one instead considers enriched categories on the right side and C module categories without an additive generator, it generalizes some quite old results in category theory on so-called action via enrichment. I should state, okay, results due to Kelly and Yanelidze and also due to Richard Wood. Okay, so let me now maybe define what a Tambara module is. In order to do that, let me first define profunctors. So given categories A and B, a profunctor phi from A to B is just a functor from B of tensor A to vector spaces. Equivalently, via just some tensor hom, it's a functor from A to the category of k-linear functors from B op to vector spaces, i.e. k-linear presheaves. So I should have mentioned this a very long time ago by now. K throughout is a fixed field, just to be clear. Okay. Similarly, a Tambara module is a profunctor between module categories over some fixed monoidal category C, together with structure maps, which go from, say, phi nm to phi w acts on n, w acts on m, which these maps should satisfy some additional axioms. And a theorem of Shimizu tells us that equivalently, this is a lax C module functor from M to the free co-completion of N, or the category of presheaves on N. This is actually the initial motivation for the name profunctor. It's a functor to a suitable, like the free co-completion of its domain. Okay, moreover, profunctors can be composed via some co-end shenanigans that I don't want to get into, but in any case, we get bicategories of profunctors and of Tambara modules. And finally, maybe the most important property of profunctors for this kind of reconstruction results is that a lax module functor gives rise to a pair of profunctors. One of them is hom blank f blank, and the other is hom f blank blank, and they are adjoint. So since I have a bicategory of Tambara modules, I can speak of adjoint one morphisms, and these profunctors are adjoint. So this is quite good because the whole internal hom situation required us to have a right adjoint. So if we want to work in full generality, profunctors are useful because we can pretend we have a right adjoint even if we don't necessarily have one. Indeed, if we let f be this functor of acting on x, and we compose the left adjoint and the right adjoint in this adjunction here, we get a monad, so an algebra object, in T of C, because T of C is the monoidal category of one endomorphisms in this bicategory. So it's Tambara modules, it's C Tambara modules from C to C. this becomes an algebra object, and this is the algebra object corresponding to M in the theorem of the previous slide. Okay, so if one now unwraps all the definitions and what this biequivalence entails for ideals for an algebra object in this category of Tambara modules. So, okay, what is an ideal in an algebra object? I mean, just if I have an algebra object A, I want an AA sub-bimodule object. So ideals in this reconstructing Tambara algebra object are actually the same thing as C-stable ideals in M, where a C-stable ideal in M is a collection of subspaces of home spaces. So for every pair of objects M, M prime in M, we should have a subspace J, M, M prime in the home space from M to M prime, which satisfies three conditions. The first is that if I have something in J and I precompose with, postcompose with something else, with anything else, I land in J. The second is that if I have something in J and I precompose with anything else, I again land in J. And the third is that if I have something in J and I act by something in C, since M is still a module category, again, I land in J. So if you like string diagrammatics for module categories, you may convince yourself that a C-stable ideal deserves the name, which I dare not use, of a three-sided ideal. Okay, so right now, okay, where am I going with this? So let C be a finite tensor category, and let A be an algebra object in C. Then it's a good exercise to convince oneself that the category of projective objects among module objects for A is given by direct summons, so it's this Karoubi envelope of objects of the form P tensor A, where P is a C projective. So I act by a projective on my regular module, and I get something projective in the category of modules. And another consequence of this theorem from a couple of slides ago is that C can be identified with the category of Tambara modules on C-proj, where there is a little caveat here, namely that C-proj is not a monoidal category. It does not have a unit object, unless C is semi-simple. So one has to work with semi-group categories, which generally tends to be quite horrible. However, here my objects have duals, so rigidity saves me, and we can get this result even in absence of the monoidal unit. In particular, this gives me a biequivalence between the bicategories of algebra objects and bimodules and bimodule morphisms between C and Tambara modules on C-proj. So, in view of the previous slide, where we described ideals in algebra objects in Tambara modules, we can give a different parametrization for ideals in an algebra object in C. Namely, ideals in A identify with C-proj stable ideals in proj CA. And we will use this fact to prove the following conjecture of Ettinghoff and Ostrich from 2021, which says that an indecomposable algebra object A is simple if and only if mod CA is exact, namely if all objects are C-projective, i.e. if I act by a projective, I get a projective no matter what. Okay, so we do this by defining a suitable C-proj stable ideal in proj CA. Namely, if I have two objects M and N of proj CA, I consider the morphisms from M to N such that if I act by a projective, I get something radical in the ordinary sense of the Jacobson radical of a category. So this is quite parallel to the notion of a C projective. C projective means I act by a projective, I get a projective. C radical means I act by a projective, I get something radical. Okay. So with this definition, one needs to show some preliminary lemmas. For instance, that the C radical is contained in the ordinary radical, and that it is the greatest C-proj stable nilpotent ideal in proj CA. On the level of algebra objects, one can think that if I take I tensor over A, I tensor over A, and so forth, at some point this should be 0. We recall some homological algebra. If we have an exact sequence, P1, P0, X, where P1 and P0 are projective, then P0 is a projective cover if and only if P1 is a radical morphism. And there is a lemma due to Mazurchuk and Mimitz, using a lot of Perron-Frobenius dimension calculations and action matrices and so forth, which tells us that if we have an exact sequence of this kind, where, however, instead of X, I have Q acting on X, where Q is projective, so this is the type of object I want to study, and P0 is a projective cover, then P1 is in the C radical. It's not just in the radical. So now let's prove the conjecture. Let's assume that mod CA is exact, and let P1 be in the C radical. Then Q acting on P1 is radical because that's the definition of the C radical. But that means that Q acts on P0 is a projective cover. But mod CA is exact. So Q acts on X is projective. So Q acts on P0 is an isomorphism because the projective cover of a projective is an isomorphism. But then Q acts on P1 must be 0. But if this is true for all Q, then P1 must be 0. Because I can, for instance, act with, say, projective cover of the unit object. Okay. Conversely, if the C radical is 0, and we consider again a sequence of the form P1, P0, and then Q acts on X, then P1 necessarily is in the C radical, but then it's necessarily 0. But then P0 is an isomorphism being as P1 is, well, being as the sequence is exact. and so Q acts on X is projective, and so the module category is exact. So this tells us that mod CA is exact if and only if A has no nilpotent ideals, but in the conjecture we assume that A was indecomposable, and the proper ideal in an indecomposable algebra is nilpotent, so we have established the conjecture. And that's all I have to say. Thank you.
Presenting these results, and you have been pointing out that you can apply to, in most general case, to any category with finite dimensional and infinite dimensional. So you sort of was pointing out into a generality of the constructions. But now, when you have such general constructions with such a generality that that everything works in a most general case, what does it give if you pick up some very specific, some small category or some other category, or some ring category of rings, or with some smaller things, more concrete things,
so,
and wish to apply, what will it give in a concrete known, like, examples?
Right, okay, so I presume, okay, so first of all, this last conjecture is not very general because it's kind of limited by this lemma here, which, as said, uses finite matrices and Perron-Frobenius dimensions. So I presume you refer to this theorem?
For example.
Okay. So for this theorem, one example that we've worked out just to see how the machinery kind of works is, okay, what module category can I define for any category of the form B comodules? Well, I can consider the fiber functor. I can consider the fiber functors. So there is always the action of comodules on vector spaces by just tensoring.
And the conclusion, what is the conclusion of this theorem?
The conclusion is that you can determine explicitly such a Hopf trimodule algebra, and we have calculated it. Kind of, we have an explicit presentation thereof. Well, okay, so such that this equivalence holds. But I mean, I guess the main point is that we know it explicitly, and we did this by just mimicking this very simple case. So it's quite, like, it yields itself to computations. It's not so bad in that regard.
Okay, thank you. Any further questions, remarks, comments? Yes.
Can you go back to the slide, the previous slide? Just, I'm confused about your definition of a contra module.
This is, okay, yes. So, this, I believe, in Posicielski's terminology, should be a semi-module.
Okay.
However, we already have tri-modules and ter-modules and bi-modules in the paper, and at some point there was too many Latin numbers. I didn't feel comfortable with that anymore.
Okay. Okay, thank you.
Any further comments, remarks? Okay, then let's thank the speaker again. So the next and the last speaker is last speaker is Christian Kasser. Okay, just a small, it's just small announcement for colleagues which are following online that this talk will not be streamed online due to some restrictions, and so for those who are online, the session is closed, and thank you for your participation. And for those who are in the room, please stay in the room. We will okay.